Welcome back to Simply About Earth, the channel where we explore the mysteries of our cosmos with scientific rigor and boundless curiosity. Before we dive into today's investigation, let me know in the comments where you're watching from. Are you in a major city where light pollution might hide these celestial visitors, or are you fortunate enough to have dark skies that will reveal their full glory? Your location might determine just how spectacular this year's cosmic show will appear to you. Today, we're investigating something that has astronomers checking their calculations twice. Something that shouldn't be happening according to our understanding of celestial mechanics. At this very moment, 7 comets are racing toward the Sun, all arriving within months of each other in 2025. Nothing like this convergence has ever been recorded in human history. But here's what makes this discovery truly unsettling. 3I Atlas, an object from another star system entirely, is also making its closest approach during this exact same window. The odds of this timing are astronomically small, unless something is coordinating these arrivals. What if this isn't a simple flyby, but the beginning of something far more extraordinary? Tonight, we're going to investigate every possibility, from statistical coincidence to forces operating beyond current scientific understanding. Stay until the end to discover what 3I Atlas might actually be doing to our solar system, and why this convergence has some researchers questioning everything they thought they knew about how our cosmic neighborhood operates. Throughout this investigation, we'll maintain a clear separation between measurable facts and speculation. When we present orbital data, observation logs, and brightness measurements, you can trust those numbers. When we explore possibilities that venture beyond confirmed science, we'll mark them clearly. This isn't about pushing theories, it's about following evidence wherever it leads. In a typical year, we might see 1, maybe 2 bright comets worth discussing. Most years pass with nothing more spectacular than a few telescopic smudges that excite only the most dedicated comet hunters. But 2025, it's like the universe decided to throw us a parade. Let me introduce you to the cast of characters that has astronomers around the world recalculating probability tables. Pan-STARRS, SWAN, Stereo, Atlas K1, Atlas G3, Lemon, and Neowise, 7 distinct comets, each carrying ice and rock from the outer reaches of our solar system, all arriving within months of each other like some cosmic reunion nobody planned. Think of it this way. Imagine if 7 different friends from across the country all showed up at your door on the same weekend, each claiming they had no idea the others were coming. Possible? Sure. Coincidental? Absolutely. Suspicious enough to make you wonder if someone sent out invitations behind your back? You bet. This clustering creates what astronomers call a swarm effect. Multiple comets crowding into a relatively short observation window. From Earth's perspective, it looks almost orchestrated, almost like something herded them here. The statistical improbability becomes immediately apparent when you visualize typical comet arrivals. Picture a chart showing comet discoveries spread across decades, dots scattered randomly across time like raindrops on pavement. Now picture 2025. 7 dots clustered together like someone dropped a handful of marbles. The pattern jumps out immediately. Most years, amateur astronomers spend months hunting for anything worth photographing. This year they're spoiled for choice. Photography forums buzz with images of multiple comet tails streaking across the same patch of sky. Social media explodes with time-lapse videos showing what looks like a coordinated celestial ballet. But here's where our investigation takes a truly intriguing turn. While these 7 comets dance their predictable orbits, something else prowls the darkness between planets. 3I Atlas, the 3rd confirmed interstellar object ever detected in our solar system. Unlike our 7 comet welcoming committee, this visitor wasn't born here. It formed around another star in another planetary system, and it's passing through our neighborhood on a one-time hyperbolic trajectory. The timing raises questions that keep astronomers awake at night. Is it pure coincidence that our solar system's most unusual comet year in recent memory coincides with a visit from an interstellar stranger, or could there be something more deliberate at work? Our test is simple but rigorous. If 3I Atlas is somehow connected to this 7 comet swarm, that connection should leave observable signatures, timing correlations that exceed statistical probability, orbital relationships that suggest more than coincidence, physical interactions that can be measured and verified. We're not looking for subtle hints or vague patterns that require creative interpretation. We're hunting for concrete, quantifiable evidence that would convince the most skeptical astronomer, the kind of data that transforms speculation into scientific fact. The stakes of this investigation extend far beyond academic curiosity. If these 7 comets arrived independently, following nothing but the cold mathematics of orbital mechanics and the random discoveries of survey telescopes, then we're witnessing a remarkable but perfectly natural celestial coincidence. The universe is vast enough to occasionally surprise us with clustering that feels meaningful but isn't. However, if some external influence, whether gravitational, electromagnetic, or something we haven't considered, has nudged these objects toward a synchronized arrival, then we're looking at evidence of forces operating on scales we barely comprehend. Forces that could reshape our understanding of how objects move through space. Consider the implications. 7 comets don't just happen to converge without reason. In a solar system governed by the predictable laws of physics, every orbit tells a story. Every trajectory carries the fingerprints of the forces that shaped it. If something guided these objects into their current paths, those fingerprints should be detectable. The interstellar visitor adds another layer of mystery. 3i Atlas carries ice and dust forged in the fires of a distant star, seasoned by cosmic radiation during a journey that likely spanned millions of years. Its chemical composition holds clues about planetary formation in other solar systems. Its behavior as it approaches our Sun reveals how materials from elsewhere respond to stellar heat. But what if its arrival isn't as random as we assumed? What if the same force that potentially herded 7 Earth-borne comets also guided an interstellar visitor toward our solar system at precisely the right moment? The questions multiply like fractals, each answer spawning new puzzles. How would we even detect such influence? What kind of mechanism could operate across the vast distances of space to coordinate objects with such precision? And if such coordination is possible, what does that tell us about the true nature of our cosmic neighborhood? As we prepare to examine each member of this unusual 7-comet cast, remember that the universe rarely reveals its secrets easily. Every discovery begins with an observation that doesn't quite fit the expected pattern. Every breakthrough starts with someone asking why things aren't quite as simple as they appear. The swarm has arrived, and with it, questions that may challenge everything we think we know about how our solar system works. But first, we need to meet our 7 visitors properly and understand what makes each one unique. Coincidence or connection? The evidence awaits, and it's time to start measuring. Let's meet our 7 visitors individually, because each carries its own story of discovery and cosmic journey. Think of this as a lineup where every suspect has an alibi, but somehow they all ended up at the same crime scene. Pan-STARRS takes center stage as our first and brightest performer. Discovered by the Panoramic Survey Telescope and Rapid Response System, a Hawaiian-based sky patrol that's revolutionized comet hunting, this object promises to reach naked-eye visibility for Northern Hemisphere observers. The timing window stretches from late March through May of 2025, giving us months to study its approach. What makes Pan-STARRS particularly intriguing isn't just its brightness potential, but its orbital geometry. The comet's path brings it relatively close to Earth's orbital plane, making it easily visible from populated latitudes. For pattern-seeking minds, this accessibility feels almost convenient. Too convenient perhaps for something that supposedly wandered in from the outer reaches of the Oort cloud entirely by chance. SWAN presents a different discovery story altogether. The Solar Wind Anisotropies spacecraft, designed to study solar particle streams, accidentally became a comet hunter when its hydrogen detection instruments began spotting the characteristic glow of comet atmospheres. SWAN comets often appear suddenly in the data, their hydrogen emissions announcing their presence before optical telescopes catch up. This hydrogen signature tells us something important about SWAN's activity level. Unlike dormant rocks that only brighten when solar heat awakens them, SWAN was already outgassing when discovered. It's been active for months, possibly years, creating that telltale hydrogen envelope that betrayed its location. For a comet allegedly following a random orbit, it seems remarkably prepared for its solar system debut. Stereo offers perhaps the most dramatic discovery narrative. Solar observation spacecraft positioned to monitor our star's activity caught this comet diving toward the Sun in their peripheral vision. Stereo comets often become suicidal solar grazers, racing so close to our star that they either disintegrate in spectacular fashion or emerge fundamentally altered by the experience. The timing here deserves attention. Stereo's arrival window coincides with a period of heightened solar activity, when our star's magnetic field is particularly turbulent. Coincidence? Or does something about solar maximum create conditions that draw objects from the outer system inward? The correlation feels too neat to ignore completely. Atlas K1 carries the weight of astronomical hype and disappointment. When the Asteroid Terrestrial Impact Last Alert System first detected this object, early brightness predictions suggested it might become one of the most spectacular comets in decades. Reality, as usual, proved more modest. Atlas K1 will likely require binoculars or a small telescope for comfortable viewing. But here's what makes Atlas K1 suspicious in our investigation. Its discovery date places it squarely within the swarm timeline, yet its orbital characteristics suggest it's been following this path for thousands of years. Why are we finding it now? Why this year when 6 other comets crowd the same observation window? Atlas G3 shares the same survey heritage as its K1 sibling discovered by the same Hawaiian telescope system that's become remarkably efficient at finding potentially hazardous objects. The Atlas survey operates like a cosmic early warning system, scanning the entire visible sky every few nights, looking for anything that moves against the background stars. What troubles careful observers is how many recent comet discoveries trace back to Atlas operations. Not because the system is flawed, quite the opposite. Atlas represents cutting-edge asteroid and comet detection technology, but when the same survey system discovers multiple members of an unusual swarm, patterns start to emerge that demand explanation. Comet Lemon brings a different pedigree to our cosmic gathering. The Catalina Sky Survey Station on Mount Lemmon in Arizona has been hunting near-Earth objects since the 1990s, accumulating one of the most comprehensive databases of small solar system bodies ever compiled. Lemon discoveries carry the authority of decades of careful observation and orbital determination. The visual expectations for Lemon remain modest, likely a binocular object at best, but its position in our swarm sequence is precisely what makes it interesting. Lemon arrives in the middle of the pack, neither leading nor trailing the group. It's positioned like a placeholder, maintaining formation with mathematical precision that seems unlikely to emerge from purely random orbital mechanics. Neowise rounds out our septet with a touch of historical irony. The Near-Earth Asteroid Tracking Program ended operations in 2007, but comets discovered during its active years continue arriving on schedule, following orbits calculated decades ago. Neowise represents the legacy of systematic sky surveys, proof that patient observation eventually pays dividends. What makes Neowise's participation in our swarm particularly noteworthy is the time delay between discovery and arrival. This comet has been tracked for over 15 years. Its orbit refined through thousands of observations. There's no uncertainty about its path, no surprises about its timing. Neowise was always going to arrive in 2025. The question is why it's arriving alongside 6 companions. When we plot all 7 orbits on a single timeline, the clustering becomes undeniable. These aren't objects discovered in 2025 that happen to be visible now. These are comets discovered across different years by different surveys using different detection methods, all converging on the same narrow time window. The diversity of discovery circumstances makes the timing coincidence even more remarkable. Hydrogen emissions, solar observations, asteroid surveys, and dedicated comet hunts all contributed different pieces to this puzzle. It's as if the universe deliberately scattered clues across multiple detection methods to ensure we'd eventually notice the pattern. Consider the sheer statistical improbability. Comet discoveries follow a roughly random distribution across time, with occasional clusterings that rarely exceed 2 or 3 objects. 7 comets arriving within months of each other represents a statistical outlier that demands explanation. Yet here they are, each following orbits calculated with the precision that only gravitational mechanics allows. No margin for error, no room for creative interpretation. These paths were set millions of years ago when our 7 visitors began their long fall toward the inner solar system. The question that haunts every careful observer is simple. What set these paths in motion with such apparent coordination? What force operating across the vast distances and timescales of the outer solar system could nudge 7 different objects towards synchronized arrivals? We're not asserting coordination. We're documenting the pattern that makes such coordination seem worth investigating. Because while each individual comet follows perfectly natural laws of motion, Their collective behavior suggests something that transcends coincidence. But before we can evaluate any connection to our interstellar visitor, we need to understand why this level of clustering strikes experienced astronomers as genuinely unusual, and that requires examining what normal comet years actually look like. Walk into any planetarium on a typical year and ask about visible comets. The astronomer will probably sigh, check their database, and tell you about one marginal object that requires a good telescope and dark skies. Maybe, if you're lucky, there's a binocular comet that dedicated enthusiasts are tracking. Most years pass without a single naked-eye comet gracing our skies. This is the baseline reality of comet watching: patience, disappointment, and occasional rewards that require serious equipment to appreciate. The general public remains blissfully unaware of the dim, fuzzy patches that excite amateur astronomers. Comets, for most people, exist only in history books and disaster movies. 2025 shatters this pattern with the subtlety of a cosmic sledgehammer. 7 notable comets within months of each other, multiple objects bright enough to photograph with ordinary cameras, several reaching binocular visibility with at least one promising naked-eye spectacle for casual observers. To understand how unusual this clustering really is, we need to examine the mathematics of comet discovery and visibility. Modern sky surveys have revolutionized our ability to detect distant objects, but they haven't changed the fundamental physics that determines when comets become bright enough to notice. The Panoramic Survey Telescope and Rapid Response System operating from Haleakala Observatory in Hawaii scans the entire available sky every few nights. The Catalina Sky Survey in Arizona covers different patches of sky with systematic precision. NEOWISE, the space-based infrared telescope, detects the heat signatures of objects invisible to ground-based instruments. These survey programs discover hundreds of new comets and asteroids every year, but the vast majority remain forever telescopic. Only a tiny fraction ever brighten sufficiently to attract public attention. The statistical expectation for any given year is 0 to 1 objects reaching naked-eye brightness, with 2 or 3 additional comets becoming accessible to serious amateur observers. Yet improved detection capabilities don't explain 2025's unusual abundance. Survey telescopes find more objects overall, but the percentage that develop into notable comets remains consistent with historical patterns. Better instruments reveal more distant, fainter objects. They don't magically create bright comets where none existed before. The key insight is that visibility depends on intrinsic properties that surveys can't change. A comet's brightness results from its size, composition, and distance from the Sun during closest approach. These characteristics were determined millions of years ago when gravitational perturbations first nudged these objects toward the inner solar system. Modern surveys simply announce arrivals that were already inevitable. We're not seeing more bright comets because we're looking harder. We're finding bright comets that were always going to arrive in 2025 regardless of our detection capabilities. This distinction matters enormously for our investigation. If survey improvements explain the clustering, we'd expect similar patterns in other recent years as telescope technology advanced. Instead, we see 2025 standing alone as an anomalous concentration of activity. The brightness reality check deserves careful attention, because media coverage often amplifies modest objects into spectacular events that disappoint casual observers. The magnitude scale works backwards. Smaller numbers indicate brighter objects. Magnitude 6 represents the limit of naked-eye visibility under pristine dark skies. Most suburban observers need binoculars to see anything dimmer than magnitude 4. Comet brightness predictions carry notorious uncertainty because outgassing rates depend on composition and solar heating in ways that resist precise calculation. Objects can brighten dramatically if they contain volatile materials that vaporize suddenly, or they can disappoint if their surfaces develop insulating dust crusts that suppress activity. Despite these uncertainties, experienced comet observers develop reliable intuitions about which objects merit attention. When veteran astronomers express surprise at 2025's crowded calendar, their reaction carries the weight of decades spent tracking dim, unremarkable objects across empty skies. The solar maximum connection adds another layer of complexity to our unusual year. Our Sun operates on an 11-year activity cycle, alternating between quiet periods with few sunspots and active phases characterized by frequent solar flares and coronal mass ejections. 2025 coincides with solar maximum when our star's magnetic field reaches peak turbulence. Solar storms can dramatically affect comet tail behavior, creating spectacular disconnection events and unusual tail geometries that make modest objects appear more active than their intrinsic brightness suggests. The enhanced solar wind during maximum also amplifies comet ion tails, potentially making our 7 visitors more photogenic than they would appear during solar minimum. But solar activity doesn't create comets, it only affects their appearance after they arrive in the inner solar system. The objects themselves were already bound for 2025 encounters, regardless of the sun's mood swings. Solar maximum might make them more spectacular to observe, but it doesn't explain why 7 different comets chose this particular year for their solar system debuts. Here's where human psychology enters the equation in ways that complicate objective analysis. Our brains evolved to detect patterns even in random data, because missing genuine patterns could prove fatal in ancestral environments. This pattern recognition capability serves us well in many contexts, but it can also lead us to perceive meaningful connections where none exist. Clustering events naturally attract attention and demand explanation. When multiple rare events occur simultaneously, we instinctively search for underlying causes rather than accepting coincidental timing. This cognitive bias becomes particularly strong when the events seem coordinated or purposeful. The 7 comet swarm triggers exactly this kind of pattern-seeking response. 7 objects arriving within months of each other feels too organized for randomness. Our intuitive sense of probability rebels against accepting such clustering as mere coincidence. Yet rigorous statistical analysis reveals that apparent clusters occur regularly in truly random distributions. Flip a coin long enough and you'll eventually see long sequences of heads or tails that feel impossible, but are mathematically inevitable. The human mind struggles to accept these clusters as natural products of randomness. The challenge for our investigation is separating legitimate statistical anomalies from the kind of clustering that feels meaningful to pattern-seeking brains but falls within normal variation. We need measurable criteria for determining when a pattern exceeds the bounds of reasonable coincidence. This is where careful orbital analysis becomes crucial. If our 7 comets share subtle gravitational influences, similar source regions, or synchronized perturbations that exceed statistical probability, then we have grounds for suspecting external coordination. If their clustering represents nothing more than the kind of apparent pattern that emerges randomly from large datasets, then coincidence becomes the most reasonable explanation. The bar for evidence must be set appropriately high. Extraordinary claims require extraordinary proof, and the assertion that something herded 7 comets into coordinated arrivals certainly qualifies as extraordinary. We need detection signatures that would convince skeptical astronomers accustomed to debunking spurious correlations. But as we prepare to examine potential mechanisms for such coordination, it's worth remembering that the universe occasionally produces genuine surprises that challenge our assumptions about how things work. Sometimes the improbable explanation turns out to be correct, and sometimes coincidences hide deeper truths waiting for careful investigation to reveal them. The swarm is real, the timing is unusual, and the questions demand answers. But what kind of force could possibly coordinate objects across such vast distances and timescales? And could our interstellar visitor provide the missing piece of this cosmic puzzle? When astronomers encounter inexplicable patterns, they reach for 2 fundamental explanations: gravity and electromagnetism. These forces govern virtually everything that moves through space, from planetary orbits to the behavior of charged particles in comet tails. If something is herding 7 comets towards synchronized arrivals, it must be operating through one of these mechanisms. Let's start with gravity, because it's the undisputed master of solar system choreography. Every object with mass warps spacetime around it, creating the invisible architecture that guides planetary orbits and comet trajectories. Gravity operates across unlimited distances with mathematical precision that allows astronomers to predict celestial events centuries in advance. But here's the critical limitation. Gravity is remarkably weak. It requires enormous masses to produce effects noticeable across interplanetary distances. The Sun, with its overwhelming gravitational dominance, shapes the broad patterns of solar system motion. Jupiter, despite being only 1,000th the Sun's mass, still manages to influence asteroid and comet orbits through its gravitational reach. For any object to gravitationally shepherd 7 comets into coordinated arrivals, it would need mass comparable to a major planet. We're not talking about subtle nudges that accumulate over millions of years. We're discussing the kind of gravitational influence that would be immediately obvious to orbital calculators studying these objects. The mathematics are unforgiving. A comet's orbital elements, its inclination, eccentricity, and timing, reflect the gravitational influences it has experienced throughout its journey. These signatures can't be hidden or disguised. If some massive object has been steering our 7 visitors, its fingerprints would be clearly visible in their orbital characteristics. Jupiter already demonstrates how real gravitational shepherding works. The giant planet has carved gaps in the asteroid belt, captured families of Trojan asteroids that follow its orbit, and redirected countless comets through gravitational encounters. We can measure these effects precisely, calculate the responsible forces, and predict future interactions with confidence. This gives us a template for detecting hidden shepherding. If some unknown massive object has influenced our 7-comet swarm, we should see consistent orbital perturbations, shared gravitational signatures, or synchronized changes that point toward a common cause. The absence of such signatures would effectively rule out gravitational coordination. Electromagnetic effects offer a different but equally constrained possibility. Comets carry electric charges as solar radiation ionizes their gas clouds, and moving charges respond to magnetic fields in measurable ways. The solar wind, that constant stream of charged particles flowing outward from our star, shapes comet ion tails and can produce dramatic disconnection events during magnetic storms. But electromagnetic forces work quite differently from gravity. They affect comet tails and atmospheric behavior without significantly altering orbital trajectories. A comet tail might twist and fluctuate in response to solar magnetic activity, but the comet itself continues following its gravitationally determined path with stubborn precision. The idea that electromagnetic fields could steer 7 comets into coordinated arrivals faces insurmountable physics problems. Such steering would require magnetic field strengths far exceeding anything observed in the solar system, and the energy requirements would dwarf the output of our sun's emissions. We're talking about forces that exist only in the immediate vicinity of neutron stars and black holes. Moreover, electromagnetic effects produce characteristic signatures in comet spectra and tail behavior that would be impossible to hide. If powerful magnetic fields were manipulating our 7 visitors, every observatory studying these objects would detect the telltale signs immediately. This brings us to the detection criteria that separates speculation from science. Real shepherding, whether gravitational or electromagnetic, must leave observable evidence that survives rigorous analysis. We need shared orbital elements that point toward common influences, consistent perturbations that exceed measurement error, synchronized anomalies that can't be explained by independent evolution. Let's apply these criteria to our 7 comet casts systematically. Do Pan-STARRS Swan, Stereo, Atlas K1, Atlas G3, Lemon, and Neowise share orbital characteristics that suggest common influences? Have their paths been shaped by forces beyond the standard gravitational environment of the solar system? The preliminary answer is disappointing for conspiracy theorists, but reassuring for conventional physics. Each comet follows an orbit consistent with independent evolution under known gravitational influences. Their source regions, orbital inclinations, and timing patterns show no evidence of coordination beyond statistical clustering that could emerge from random processes. Pan-STARRS approaches from a different direction than Swan. Stereo's solar grazing trajectory bears no resemblance to Atlas K1's more distant path. Lemon and Neowise originated in different parts of the outer solar system, and have followed distinctly different routes toward their current positions. If some hidden shepherd were coordinating these arrivals, we'd expect to see subtle but measurable correlations in their orbital evolution, common nodes where their paths intersect, similar perturbations that suggest shared influences, timing relationships that exceed the bounds of reasonable coincidence. Instead, we see 7 independent objects following 7 independent paths, converging only in the sense that they all happen to reach peak brightness during the same general time period. Their orbits tell stories of isolated journeys from different starting points, shaped by the predictable influences of solar gravity and occasional planetary encounters. This doesn't completely eliminate the possibility of external coordination, but it raises the evidentiary bar considerably. If something is herding these comets, it's operating through mechanisms so subtle that they escape detection by current observational methods. The simpler explanation, statistical clustering enhanced by improved survey capabilities, remains more consistent with available evidence. But our investigation takes an intriguing turn when we consider Three-Eyed Atlas as a potential coordinator. Unlike the 7 traditional comets, this interstellar visitor carries no obligation to follow the gravitational patterns that constrain solar system natives. Its hyperbolic trajectory and external origin make it a genuinely foreign influence in our cosmic neighborhood. Could an interstellar object, despite its small mass, somehow influence the timing or behavior of traditional comets through mechanisms we don't fully understand? The question pushes against the boundaries of conventional physics, but deserves serious consideration given the unusual circumstances. Three-Eyed Atlas's limitations as a shepherd are immediately obvious. Its estimated mass falls far short of planetary scales, making gravitational influence negligible. Its rapid passage through the solar system provides limited time for subtle perturbations to accumulate. Its trajectory doesn't intersect directly with any of the 7 traditional comets, ruling out close encounters that might produce measurable effects. Yet the timing coincidence remains troubling for those who prefer their universe free of mysterious correlations. An interstellar visitor arriving during our solar system's most active comet year in recent memory feels too convenient for pure chance. Even if Three-Eyed Atlas can't directly influence comet orbits, could its presence somehow correlate with conditions that make such clustering more likely? This question opens fascinating speculative territory while remaining anchored to observational constraints. We're not proposing invisible tractor beams or exotic physics that violate established laws. We're asking whether the arrival of an interstellar object might coincide with natural processes that enhance comet activity or detection rates. Perhaps Three-Eyed Atlas serves as an indicator, rather than a cause, a cosmic weather vane that points toward conditions favorable for comet discoveries. Maybe interstellar visitors preferentially arrive during periods when the outer solar system experiences enhanced gravitational stirring that increases the rate at which comets begin their sunward journeys. These possibilities require careful investigation rather than casual speculation, but they illustrate how seemingly impossible coordination might emerge from natural processes operating on scales we're only beginning to understand. The universe has surprised us before with subtle connections that initially seemed impossible. As we prepare to meet our interstellar suspect properly, remember that the most profound discoveries often begin with observations that don't quite fit conventional explanations. Sometimes the impossible merely waits for better instruments and more careful analysis to reveal its true nature. The alarm we're sounding isn't the shrill warning of imminent doom, it's the measured tone of scientific curiosity confronting an unexplained pattern. Think of it as a cosmic smoke detector, not a fire siren. Something unusual is happening in our celestial neighborhood, and responsible investigation demands we examine it carefully before drawing conclusions. 2025 promises to deliver the kind of sky show that transforms casual stargazers into dedicated comet hunters. Multiple bright objects developing spectacular tales simultaneously, photographic opportunities that occur perhaps once in a generation, social media filling with time-lapse videos of celestial visitors racing across star fields with almost choreographed precision. The spectacle itself poses no danger. Comets are fundamentally fragile objects, loose collections of ice, dust, and organic compounds that barely hold together under their own weak gravity. When solar heating transforms them into the glorious apparitions that capture public imagination, we're witnessing them literally falling apart in slow motion, shedding material that will never be recovered. Even the closest approaches in our 7-comet lineup remain safely distant by astronomical standards. Pan-STARRS's nearest pass takes it well beyond the Moon's orbit. Swan and Stereo follow paths that pose no conceivable threat to Earth or any other major body. These are flyby events, not collision courses. The genuine alarm comes from pattern recognition systems that evolution hardwired into human brains for survival purposes. When multiple unusual events cluster together, we instinctively search for underlying causes rather than accepting coincidental timing. This response served our ancestors well when detecting coordinated threats in natural environments. But modern humans apply this same pattern-seeking tendency to cosmic events that operate on scales vastly exceeding our intuitive understanding. We see 7 comets arriving simultaneously, and immediately wonder who sent them. What force could coordinate such precision across the vast distances of space? Why now, and why together? These questions become particularly compelling when combined with the presence of 3I Atlas, an interstellar visitor whose timing seems too convenient for pure coincidence. The narrative practically writes itself: alien probe arrives, comet swarm follows, something is clearly happening that demands immediate attention. Social media algorithms amplify this narrative because mystery and potential conspiracy generate the engagement metrics that drive platform economics. Videos suggesting hidden connections between celestial events receive more views than careful explanations of orbital mechanics and statistical probability. The story grows in the telling, fed by our collective hunger for meaning in an apparently random universe. Here's where our accountability rule becomes crucial. Every bold claim must survive rigorous testing against established physics and observed data. Speculation is allowed, even encouraged, but it must be clearly labeled and held to appropriate evidentiary standards. Entertainment value doesn't justify promoting unfounded theories as factual conclusions. The distinction between spectacle and causality deserves constant emphasis. Beautiful doesn't equal coordinated. Dramatic doesn't equal artificial. Impressive doesn't equal threatening. The universe regularly produces natural phenomena that exceed our aesthetic expectations without requiring exotic explanations. Consider how 2025's enhanced solar activity will amplify the visual impact of our comet parade. Solar maximum brings frequent coronal mass ejections and high-speed particle streams that can dramatically affect comet tail behavior. Ion tails might stretch across multiple degrees of sky during strong solar storms. Disconnection events could create the illusion of comets shedding pieces on command. These effects will generate spectacular photographs and videos that seem to show coordinated behavior among our 7 visitors. Social media will fill with imagery that appears to document synchronized tail movements, simultaneous brightening events, and other phenomena that suggest external control. The reality will be more mundane, but no less fascinating. Each comet responds independently to the same solar environment, creating apparent coordination through shared exposure to enhance solar activity. It's like watching 7 different weather vanes all point in the same direction during a windstorm, synchronized response to a common influence, not evidence of centralized control. This solar maximum timing adds another layer to our investigation. Why does our unusual comet year coincide with peak solar activity? Is there some connection between solar cycles and the rate at which comets begin their inward journeys from the outer solar system? Could gravitational or electromagnetic effects associated with solar maximums somehow influence the timing of comet arrivals? These questions push into speculative territory, but remain grounded in measurable phenomena. Solar activity follows well-documented cycles that correlate with various space weather effects. If solar maximum somehow enhances the probability of comet discoveries or arrivals, that correlation should be detectable in historical data spanning multiple solar cycles. The investigation framework we're establishing requires constant vigilance against confirmation bias, the tendency to interpret ambiguous evidence as supporting preferred conclusions. When we see unusual tail behavior, our first response should be checking for solar storm activity, not invoking exotic coordination mechanisms. When bright outbursts occur, we should examine the comet's composition and solar heating rather than assuming external triggers. When orbital anomalies appear, we should verify measurement accuracy and consider known perturbation sources before proposing unknown influences. This disciplined approach doesn't eliminate wonder or discourage legitimate speculation. It simply ensures that our sense of mystery remains calibrated to actual observations rather than wishful thinking. The universe provides enough genuine puzzles without requiring us to invent additional mysteries. The 7-comet swarm represents a legitimate statistical anomaly that merits serious attention. Such clustering occurs rarely enough to justify careful investigation of potential underlying causes. If our analysis reveals nothing beyond coincidental timing, enhanced by improved survey capabilities, that conclusion itself contributes valuable information to our understanding of solar system dynamics. But if we detect genuine correlations that exceed statistical expectations, orbital relationships, timing synchronizations, or behavioral anomalies that point toward common influences, then we've identified something that could reshape our understanding of how the solar system operates. The presence of 3I Atlas during this unusual year adds a wildcard element that transforms a statistical curiosity into a potentially profound mystery. Interstellar visitors arrive perhaps once per decade, making their timing genuinely significant rather than merely interesting. We're not claiming that 3I Atlas caused or coordinated the 7-comet swarm. We're acknowledging that the coincidence deserves investigation rather than casual dismissal. Even if no direct causal relationship exists, the correlation might reveal indirect connections that illuminate previously hidden aspects of solar system behavior. Our accountability extends beyond avoiding false alarms to ensuring we don't miss genuine signals in our eagerness to debunk unfounded theories. The history of science includes numerous examples of initially ridiculous ideas that eventually proved correct through careful investigation and accumulating evidence. The challenge is maintaining appropriate skepticism while remaining open to evidence that might contradict conventional expectations. We need rigorous standards for evaluating extraordinary claims without becoming so rigid that we reject extraordinary evidence when it finally appears. As we prepare to examine our interstellar visitor in detail, remember that the most profound discoveries often emerge from investigations that began with simple questions about unusual patterns. Sometimes the universe is trying to teach us something new, and sometimes the lesson arrives disguised as coincidence. The swarm has sounded its alarm, and we're responding with the tools of scientific inquiry rather than the reflexes of panic. Whatever answers await, they'll emerge from careful measurement and analysis rather than speculation and assumption. But first we need to understand our prime suspect, the interstellar stranger whose timing has raised so many questions. 3I/ represents the third confirmed interstellar object to pass through our solar system, a cosmic wanderer that formed around another star and is now making a one-time hyperbolic flyby through our celestial neighborhood. Unlike every other object we've discussed, this visitor carries no local birth certificate. It's genuinely alien in the most literal sense possible. The significance of this distinction cannot be overstated. Every comet in our 7-member swarm originated within our solar system's gravitational embrace, forged from the same primordial materials that built planets and moons 4.5 billion years ago. 3I Atlas carries ice and dust that condensed around a different star in a different stellar nursery, under conditions we can only imagine. Think of it as receiving a message in a bottle from another shore, except the bottle traveled not across an ocean, but across the vast gulf between stellar systems. The journey likely consumed millions of years, during which our visitor drifted through the near-perfect vacuum of interstellar space, bombarded by cosmic radiation and gradually accumulating the chemical signatures of its epic voyage. Most importantly for our investigation, 3I Atlas poses no collision threat to Earth. Its trajectory carries it safely past all major planetary bodies, following a hyperbolic path that will eventually sling it back into interstellar space, never to return. This is a reconnaissance mission, not an invasion, assuming of course that missions and invasions are relevant concepts for what might simply be a wandering chunk of ancient ice. The comet-like behavior of 3I Atlas adds layers of complexity to its story. Far from the Sun, where temperatures should keep any ice frozen solid, this object has developed a detectable coma and tail. Solar heating shouldn't be sufficient at such distances to drive the kind of outgassing that creates visible comet activity. Yet observations clearly show the characteristic fuzzy appearance that distinguishes active comets from inert asteroids. This premature activity suggests either an unusual composition, perhaps containing supervolatile materials that vaporize at extremely low temperatures, or some internal heat source that drives outgassing independently of solar warming. Both possibilities offer tantalizing clues about conditions in the stellar system where 3I Atlas originated. The scientific excitement surrounding any interstellar visitor stems from its unique status as a direct sample of another planetary system. Every measurement we make, spectroscopic analysis of its chemical composition, photometric monitoring of its brightness variations, astrometric tracking of its precise trajectory, provides information about stellar formation processes beyond our Sun's influence. But our investigation focuses on a different question entirely. Could this interstellar stranger somehow be connected to the unusual timing of our 7-comet swarm? The correlation might be purely coincidental, but the stakes are high enough to justify careful investigation rather than casual dismissal. If a genuine connection exists between 3I Atlas and our 7 traditional comets, it would manifest through observable signatures that survive rigorous analysis, timing correlations that exceed statistical probability, orbital relationships that suggest more than coincidence, behavioral anomalies that point toward shared influences rather than independent evolution. The absence of such signatures would argue strongly against any connection, leaving us with an interesting but ultimately meaningless coincidence. The presence of clear correlations, however, would open profound questions about forces operating on scales we barely comprehend. Consider the implications of discovering that an interstellar visitor can somehow influence the behavior of solar system natives. Such capability would suggest interaction mechanisms far more subtle and far-reaching than current physics predicts. It would hint at connections between stellar systems that transcend the simple gravitational relationships we currently understand. Even without invoking exotic physics, the timing correlation between 3I Atlas and our comet swarm deserves serious attention. Interstellar objects arrive rarely, perhaps once per decade, based on current detection rates. Their visits should be randomly distributed across time, uncorrelated with internal solar system events. Yet here we have an interstellar visitor arriving during our most unusual comet year in recent memory. The probability calculation is straightforward. If interstellar arrivals and comet swarms are independent events, their simultaneous occurrence should be proportionally rare. The more unusual each individual event, the more suspicious their coincidence becomes. Of course, correlation doesn't imply causation, and suspicious timing doesn't constitute proof of connection, but it does justify the kind of detailed investigation we're undertaking. If the universe is trying to teach us something about previously unknown relationships between interstellar and local objects, we need to be listening carefully enough to hear the lesson. The brightness expectations for 3I Atlas require careful management to avoid later disappointment. Unlike the potentially spectacular members of our 7-comet swarm, this interstellar visitor will likely remain a telescopic object throughout its passage. Its scientific importance far exceeds its visual impact for casual observers. Professional and amateur astronomers worldwide are coordinating observation campaigns to maximize the scientific return from 3I Atlas's brief visit. Every photon of light we collect from this object represents irreplaceable information about conditions in another stellar system. We won't get another chance to study this particular visitor. Its hyperbolic trajectory ensures a one-time flyby with no possibility of return. The observational campaign also provides our best opportunity to detect any connection between 3I Atlas and the 7-comet swarm. If shared anomalies exist, synchronized brightness variations, correlated tail behavior, or timing relationships that exceed coincidence, they should become apparent through careful monitoring of all 8 objects simultaneously. The challenge lies in distinguishing genuine correlations from the kind of apparent patterns that emerge when human brains analyze complex datasets. Pattern recognition systems that evolve to detect meaningful relationships in noisy environments sometimes identify structure where none exists, particularly when we're strongly motivated to find connections. This is why our investigation maintains strict separation between observation and interpretation. When we measure brightness variations, orbital elements, or spectroscopic properties, those numbers represent objective reality. When we explore potential relationships between those measurements, we enter the realm of hypothesis testing, where skepticism must balance curiosity. The scientific method provides tools for navigating this balance. Statistical analysis can quantify the probability that observed correlations result from random chance rather than genuine relationships. Independent verification ensures that apparent patterns survive scrutiny by multiple research groups using different instruments and techniques. But even the most rigorous analysis requires human judgment about what constitutes sufficient evidence for extraordinary claims. The assertion that an interstellar visitor influences solar system comet behavior clearly qualifies as extraordinary, demanding proportionally strong evidence to justify serious consideration. As we prepare to examine 3I Atlas's orbital characteristics and predicted behavior, remember that the stakes of this investigation extend far beyond resolving a curious coincidence. If genuine connections exist between interstellar visitors and local solar system dynamics, such discovery would fundamentally alter our understanding of how stellar neighborhoods interact across the vast distances of space. The universe may be more interconnected than our current theories suggest, with subtle influences operating on scales that dwarf human intuition, or it may simply be offering us an interesting statistical fluke that tests our ability to distinguish pattern from coincidence. Either way, the answer lies in the data, and it's time to examine our interstellar suspect more closely. The stranger has arrived, and its story is written in the geometry of its approach. The trajectory of 3i Atlas reads like a cosmic passport, documenting a journey that began in interstellar space and will end there as well. Unlike the elliptical orbits that trap planets and traditional comets in endless cycles around the Sun, this visitor follows a hyperbolic path, the mathematical signature of an object with enough velocity to escape our solar system's gravitational embrace forever. Picture a slingshot trajectory that dives toward the Sun from the depths of space, swings around our star in a sharp curve, then accelerates back toward interstellar darkness. No return visits, no second chances for observation. 3i Atlas gets one pass through our neighborhood, and we're witnessing it in real time. The orbital elements tell a fascinating story about origins and destinations. The object approaches from a direction roughly consistent with the constellation Perseus. Though interstellar space contains no road signs to mark its specific starting point, its hyperbolic excess velocity, the speed it maintains even after escaping solar gravity, suggests a journey spanning hundreds of thousands of years from the nearest candidate star systems. What makes this trajectory particularly intriguing is its inclination relative to the ecliptic plane, the flat disk that contains planetary orbits and most solar system debris. 3i Atlas places at a modest angle rather than plunging in from high above or below the planetary plane. This near-ecliptic geometry means the object passes relatively close to the orbital paths where our 7 comet swarm members spend their time. The inclination angle deserves careful attention, because it affects the probability of gravitational interactions with solar system objects. A visitor arriving from high galactic latitudes would sweep through our planetary system with minimal opportunity to influence local dynamics. But 3i Atlas's more moderate inclination keeps it within the general vicinity of planetary and comet orbits for an extended period. This doesn't mean close encounters are occurring. The distances involved still measure in astronomical units, far beyond the reach of direct gravitational influence. But it does mean that 3i Atlas spends months moving through the same general region of space where our 7 traditional comets are executing their own solar approaches. The retrograde nature of 3i Atlas's motion adds another layer of geometric complexity. While most solar system objects orbit the Sun in the same direction the planets rotate, our interstellar visitor approaches from the opposite direction. This retrograde motion creates relative velocities that exceed what any solar system native experiences during normal gravitational encounters. High relative velocities typically minimize gravitational effects, because fast-moving objects spend less time within each other's gravitational influence zones. If 3i Atlas was somehow affecting traditional comet orbits, the retrograde motion would actually work against such interaction by reducing the duration of any potential encounters. These orbital characteristics establish important constraints for our investigation. Any influence 3i Atlas might exert on the 7 comet swarm must operate through mechanisms that don't require close approaches or extended gravitational interaction times. Direct shepherding through conventional celestial mechanics appears increasingly unlikely as we examine the geometric details. But geometry alone doesn't eliminate all possibilities for connection. The timing correlations between 3i Atlas's key orbital events and unusual behavior in our 7 comet cast could reveal influences that transcend simple gravitational calculations. Consider the significance of orbital nodes, the points where 3i Atlas's trajectory crosses the ecliptic plane. These crossings represent moments of closest approach to the general region occupied by traditional comets and their associated debris trails. If any interaction between interstellar and local objects occurs, these nodal passages provide the most likely opportunities. The ascending and descending nodes of 3i Atlas occur at specific dates that can be calculated with astronomical precision. If these dates correlate with unusual activity in our 7 comet swarm, brightness outbursts, tail anomalies, or orbital perturbations, such correlation would constitute genuine evidence for some form of connection. The challenge lies in defining what constitutes unusual activity in a context where comet behavior naturally includes considerable variation and unpredictability. Brightness fluctuations, tail development, and even minor orbital changes occur routinely as comets respond to solar heating and outgassing forces. The bar for evidence must be set high enough to exclude normal comet behavior from consideration. Statistical analysis provides tools for addressing this challenge objectively. If we monitor our 7 traditional comets continuously and catalogue all instances of brightness changes, tail events, or other notable behavior, We can then test whether such events cluster around Three-Eyed Atlas's key orbital dates more frequently than random chance would predict. The null hypothesis that Three-Eyed Atlas and the seven-comet swarm are unrelated predicts that unusual events should be distributed randomly across time, uncorrelated with the interstellar visitor's orbital milestones. Any significant deviation from random distribution would argue for some form of connection, even if the mechanism remains unclear. But we must also guard against selection bias, the tendency to focus on apparent correlations while ignoring instances where expected patterns fail to appear. A rigorous investigation requires tracking all potentially relevant events, not just those that seem to support preferred conclusions. The orbital evolution of Three-Eyed Atlas provides additional opportunities for testing potential connections. As the object approaches perihelion, solar heating should drive increased outgassing activity that might trigger corresponding responses in other objects if some form of communication or coordination mechanism exists. The predicted brightness curve for Three-Eyed Tat shows steady brightening as it approaches the Sun, potentially punctuated by sudden outbursts if volatile materials vaporize rapidly or if internal structures fragment under thermal stress. Each of these events occurs at predictable times and locations along the orbital path. If the seven-comet swarm somehow responds to Three-Eyed Atlas's activity, those responses should occur at times that correlate with the interstellar visitor's predicted brightening events. The tighter the temporal correlation, the stronger the evidence for genuine connection rather than coincidental timing. However, we must also consider the possibility that apparent correlations result from shared responses to common external influences rather than direct interaction between objects. Solar activity, interplanetary magnetic field variations, or other space weather phenomena might affect all comets simultaneously, creating the appearance of coordination without requiring direct communication between objects. This solar influence hypothesis predicts that any correlated behavior should be traceable to specific space weather events, solar flares, coronal mass ejections, or high-speed particle streams that interact with comet atmospheres in measurable ways. The presence of such solar triggers would argue against exotic coordination mechanisms in favor of conventional astrophysical processes. The orbital characteristics of Three-Eyed Atlas also constrain the duration of any potential influence on solar system objects. The visitor's hyperbolic trajectory ensures a brief passage through our neighborhood, perhaps 18 months from initial detection to final departure beyond observational reach. This limited interaction time means that any effects on the seven-comet swarm must manifest relatively quickly and be detectable with current instrumentation. Subtle influences that accumulate over decades or centuries would remain invisible during Three-Eyed Atlas's brief visit. As we examine the specific predictions for perihelion passage, remember that orbital mechanics operates with clockwork precision regardless of the exotic possibilities we're investigating. Three-Eyed will reach its closest solar approach at a time and location determined by gravitational forces that care nothing for human speculation about alien coordination or interstellar communication. The numbers don't lie, and the geometry tells its own story, but whether that story includes connections to our seven-comet swarm remains an open question that perihelion may finally answer. Perihelion represents the moment of truth for any comet, the closest approach to our Sun when months or years of gradual approach suddenly accelerate into a crescendo of activity. For Three-Eyed Atlas, this milestone carries particular significance because it marks the point where an interstellar visitor experiences the full intensity of our star's radiation and particle output. The physics of perihelion are both predictable and dramatic. As Three-Eyed Atlas draws closer to the Sun, solar radiation intensifies according to the inverse square law, doubling in brightness and heating power with each halving of distance. Ice that remained frozen during the long interstellar journey begins to vaporize, creating the gas and dust envelope that transforms a dark, inert chunk into a glowing, active comet. But the composition of interstellar ice likely differs from the water-dominated mixtures that characterize solar system comets. Three-Eyed Atlas formed in the outer regions of another stellar system where temperatures and chemical conditions might have favored different molecular species. Carbon monoxide, carbon dioxide, methane, and more exotic compounds could dominate its makeup. These compositional differences should reveal themselves through spectroscopic analysis during perihelion passage. Each molecular species produces characteristic emission lines when vaporized and excited by solar radiation. The spectrum of 3I Atlas will essentially serve as a chemical fingerprint of its birth environment, preserved across millions of years of interstellar travel. If our investigation uncovers genuine connections between 3I Atlas and the 7-comet swarm, perihelion provides the most likely window for dramatic revelations. The intense solar heating that drives peak comet activity might also trigger whatever mechanisms could coordinate behavior among multiple objects. The observable signatures we need to watch for are both subtle and dramatic. Sudden brightness increases often mark the vaporization of particularly volatile materials or the exposure of fresh ice surfaces as protective dust crusts erode away. These outbursts can boost a comet's brightness by factors of 10 or more within hours, creating spectacular observing opportunities while providing clues about internal composition and structure. Jets of material streaming from specific locations on 3I Atlas's nucleus could create asymmetric thrust effects that slightly alter the comet's trajectory. These non-gravitational forces are well-documented phenomena in traditional comets, but their presence in an interstellar visitor would provide unprecedented insights into how materials from other stellar systems respond to our Sun's influence. The development of 3I Atlas's tail system deserves particular attention because it offers real-time visualization of the interaction between interstellar material and solar wind. Ion tails form when solar ultraviolet radiation ionizes comet gases, creating charged particles that stream away from the Sun under the influence of the solar magnetic field. The behavior of this ion tail, its length, orientation, and response to solar wind variations will reveal how gases from another stellar system interact with our Sun's particle output. Any unusual characteristics compared to traditional comet tails might hint at compositional differences that distinguish interstellar from local materials. Dust tails follow different physics, shaped by radiation pressure rather than magnetic forces. The size, distribution, and composition of dust particles determines how dramatically solar radiation can deflect them from ballistic trajectories. Large particles barely deviate from their original paths, while microscopic grains can be pushed into sweeping curved tails that stretch across degrees of sky. If 3I Atlas produces an unusually spectacular dust tail, it might indicate a composition rich in fine particles that respond strongly to solar radiation pressure. Alternatively, fragmentation during perihelion passage could suddenly release large quantities of dust that were previously locked within the comet's interior structure. Fragmentation events represent the most dramatic possible outcome of perihelion passage. The combination of solar heating, rotational stress, and internal pressure from vaporizing volatiles occasionally proves too much for a comet's weak gravitational binding. The object breaks apart, sometimes splitting into multiple fragments that separate along the orbital path. For 3I Atlas, fragmentation would be particularly significant because it would provide access to interior materials that have remained unaltered since the comet's formation in another stellar system. The fresh surfaces exposed by breakup would offer unprecedented opportunities for spectroscopic analysis of truly pristine interstellar materials. But fragmentation could also complicate our investigation of potential connections to the 7-comet swarm. Multiple fragments following slightly different trajectories might create the appearance of coordinated behavior where none exists, simply through the geometric complexity of tracking several related objects simultaneously. The solar wind environment during 3I Atlas's perihelion passage adds another variable that could influence both the interstellar visitor and any potential connections to other comets. Solar maximum conditions mean enhanced particle densities, stronger magnetic fields, and more frequent coronal mass ejections that can dramatically affect comet tail behavior. These space weather effects create spectacular visual phenomena, tail disconnections, plasma instabilities, and magnetic reconnection events that can make comet tails appear to twist, kink, or break apart entirely. Such events occur independently in each comet's immediate environment, but they respond to the same solar triggers, potentially creating apparent coordination where none exists. The key to distinguishing genuine coordination from shared response to solar conditions lies in timing precision and geometric analysis. Solar wind disturbances propagate outward from the Sun at predictable velocities, reaching different comet locations at calculable times. If unusual behavior in our 7-comet swarm correlates with 3I Atlas events but cannot be explained by solar wind propagation delays, that correlation becomes significantly more interesting. Amateur astronomers worldwide are preparing observation campaigns to monitor 3I Atlas through its perihelion passage, providing distributed coverage that no single observatory could match. This citizen science network will generate continuous light curves, photographic documentation of tail development, and real-time alerts if dramatic outbursts or fragmentation events occur. The observational coordination extends to professional facilities as well, with space-based telescopes, ground-based observatories, and specialized comet hunting surveys all contributing to the most comprehensive study of an interstellar visitor ever attempted. Every photon of light we collect represents irreplaceable scientific data about conditions in another stellar system. But our investigation requires parallel monitoring of all 7 traditional comets during the same period, looking for behavioral anomalies that might correlate with 3I Atlas events. This comparative approach will help distinguish between normal comet variability and potentially significant correlations that exceed statistical expectations. The precision required for detecting subtle correlations pushes current observational capabilities to their limits. Small brightness variations, minor tail asymmetries, or slight orbital perturbations might provide the only evidence of exotic interactions operating below the threshold of conventional detection methods. As perihelion approaches, remember that the universe operates according to physical laws that remain constant regardless of our hopes for dramatic discoveries. 3I Atlas will brighten, develop tails, and potentially fragment based on its intrinsic properties in response to solar heating, not on any agenda to provide spectacular revelations for human observers. Yet within those natural processes lie opportunities for profound discoveries about the nature of interstellar materials and their behavior in solar environments. Whether those discoveries include evidence of connections to our 7-comet swarm remains an open question that only careful observation can answer. The cosmic clockwork continues its precise operation, indifferent to speculation but faithful in providing the data we need to distinguish between wishful thinking and genuine revelation. Our sun operates on cycles that dwarf human attention spans, alternating between periods of relative calm and phases of dramatic activity with the regularity of a cosmic metronome. The 11-year solar cycle that governs this behavior is reaching its peak in 2025, transforming our star into a more volatile and visually spectacular version of its usual self. Solar maximum brings an abundance of sunspots, those dark patches that mark regions where intense magnetic fields break through the sun's surface. These magnetic field concentrations store enormous amounts of energy that occasionally release explosively, hurling charged particles and electromagnetic radiation into space at speeds that cross the solar system in hours or days. For our 7-comet investigation, this enhanced solar activity creates both opportunities and complications. The increased particle density and stronger magnetic fields of solar maximum can dramatically amplify comet tail behavior, making modest objects appear far more spectacular than they would during quieter solar periods. Consider how a coronal mass ejection, a billion-ton bubble of magnetized plasma hurled from the sun's corona, interacts with a comet's delicate ion tail. The shockwave and magnetic field distortions can compress, twist, or completely sever the tail in events that unfold over hours and create some of the most dramatic comet photography possible. These tail disconnection events occur when the magnetic field carried by solar wind undergoes rapid polarity changes that cannot be accommodated by the comet's existing tail structure. The old tail is abandoned, drifting away as space debris, while a new tail begins forming in the restructured magnetic environment. To observers unfamiliar with space weather physics, these events can appear almost supernatural. A comet's tail might suddenly develop kinks, knots, or spiral structures that seem to violate the simple physics of gas streaming away from a central source. The tail might appear to break off entirely, creating the illusion that something has attacked or damaged the comet. In reality, these phenomena represent normal responses to abnormal solar conditions. The comet itself remains unaffected. Only its gossamer tail of ionized gas responds to the changing magnetic environment. But the visual impact can be so dramatic that observers inevitably search for exotic explanations rather than accepting conventional space weather as the cause. This solar influence becomes particularly relevant to our investigation because all 8 objects in our study, 7 traditional comets plus 3I Atlas, share the same space weather environment. They all experience the same coronal mass ejections, the same high-speed particle streams, and the same magnetic field variations that characterize solar maximum conditions. If dramatic tail events occur simultaneously across multiple comets, the most straightforward explanation involves shared response to common solar triggers, rather than mysterious coordination between the objects themselves. A single large solar storm can affect comet tails throughout the inner solar system, creating apparent synchronization that has nothing to do with communication or coordination between comets. The enhanced solar activity of 2025 also affects Earth's magnetosphere in ways that amplify the perceived drama of our comet year. Geomagnetic storms driven by solar particle impacts can disrupt satellite communications, interfere with GPS navigation, and even threaten electrical power grids in extreme cases. More visibly, these storms push the aurora zones toward lower latitudes, allowing observers at moderate geographic locations to witness the dancing lights typically reserved for polar regions. The combination of active comets and active aurora creates a sky show that feels almost supernatural in its intensity and timing. But it's crucial to separate cause from correlation in these relationships. Solar storms affect both comet tails and Earth's magnetosphere, but comets don't cause geomagnetic disturbances. The Sun drives both phenomena independently, creating coincident effects that share common timing without implying any causal relationship between comets and terrestrial impacts. This distinction becomes vital when evaluating claims about connections between 3I Atlas and various Earth-based phenomena. If satellite systems fail or power grids experience disruptions during the interstellar visitor's passage, solar activity provides a far more plausible explanation than exotic influence from a small, distant comet. The timing of solar maximum relative to our unusual comet year raises intriguing questions about potential correlations between solar cycles and comet discovery or arrival patterns. Could enhanced solar activity somehow influence the rate at which comets begin their inward journeys from the outer solar system? Might gravitational or electromagnetic effects associated with solar maximum affect the timing of comet arrivals? These questions venture into speculative territory, but remain grounded in measurable phenomena. Solar activity follows well-documented cycles that should leave detectable signatures in comet arrival statistics, if genuine correlations exist. Historical data spanning multiple solar cycles could reveal whether active solar periods coincide with enhanced comet activity more frequently than random chance predicts. The investigation requires careful separation of solar effects from any potential connections between 3I Atlas and our 7-comet swarm. When unusual tail behavior occurs, our first response should involve checking space weather monitoring systems for coronal mass ejections, high-speed solar wind streams, or other documented solar triggers. Only after accounting for known solar influences can we legitimately consider more exotic explanations for observed phenomena. This methodical approach helps prevent the kind of premature conclusions that arise from ignoring conventional causes in favor of sensational alternatives. Professional space weather monitoring systems provide real-time data about solar activity that allows precise correlation with observed comet behavior. The Solar and Heliospheric Observatory, the Solar Dynamics Observatory, and ground-based magnetometer networks continuously track solar conditions and their propagation through interplanetary space. This monitoring infrastructure gives us unprecedented ability to distinguish between solar-driven comet behavior and genuinely anomalous events that might indicate other influences. If 3I Taurus loss somehow affects the behavior of traditional comets, those effects should be detectable above the background noise of normal solar variability. Amateur observers contribute crucial monitoring capabilities that complement professional space weather systems. Comet photographers worldwide document tail behavior, brightness variations, and structural changes with temporal resolution that often exceeds what busy professional observatories can achieve. This distributed observation network provides continuous coverage of our entire comet cast, creating comprehensive datasets that allow detailed correlation analysis between solar activity and comet behavior. The more complete our observational record, the more confidently we can identify genuinely unusual events that merit further investigation. The enhanced solar activity of 2025 guarantees that our comet investigation will unfold against a backdrop of frequent space weather events. This active solar environment will create numerous opportunities for spectacular comet photography while simultaneously complicating efforts to identify subtle influences that might operate independently of solar triggers. The challenge lies in maintaining appropriate standards for evidence while remaining open to genuine anomalies that might reveal previously unknown aspects of comet behavior. The universe has surprised us before, with subtle connections that initially seemed impossible, and solar maximum conditions might provide the energetic environment necessary for detecting weak interaction effects. As our investigation prepares to examine how space weather affects conditions on Earth, remember that the Sun's behavior ultimately drives most of the dramatic phenomena we associate with active comet periods. The question isn't whether solar activity influences comet behavior, that connection is well established, but whether additional influences operate alongside solar effects in ways that current theory doesn't predict. The cosmic dance continues, choreographed by magnetic fields and particle streams that connect our star to every object in its gravitational embrace. But within that familiar choreography, new steps might await discovery. The influence of space weather on Earth creates a complex web of technological vulnerabilities that most people never consider until systems start failing unexpectedly. While comets themselves pose no direct threat to our planet, the enhanced solar activity that makes comet tails spectacular can wreak havoc on the electronic infrastructure that modern civilization depends upon. Geomagnetic storms, the terrestrial response to solar particle impacts, can induce electrical currents in power transmission lines, potentially overloading transformers and triggering cascading blackouts. The March 1989 storm that collapsed Quebec's electrical grid demonstrated how space weather can translate into very earthly consequences for millions of people. Satellite systems face even more direct exposure to solar particle bombardment. High-energy protons and electrons accelerated by solar storms can penetrate spacecraft shielding, causing temporary malfunctions or permanent damage to sensitive electronics. GPS navigation, satellite communications, and weather monitoring systems all become less reliable during periods of intense solar activity. Aviation adds another layer of vulnerability, particularly for flights over polar regions where Earth's magnetic field provides less protection from cosmic radiation. Airlines routinely reroute flights during severe geomagnetic storms to avoid exposing passengers and crew to elevated radiation levels, while protecting aircraft electronics from space weather effects. These impacts create a dangerous psychological environment for evaluating claims about connections between celestial events and terrestrial problems. When comet activity peaks simultaneously with solar maximum conditions, the timing seems too convenient to be coincidental. Power outages, communication failures, and navigation problems feel like evidence of exotic influence from our unusual seven-comet swarm. The reality is more mundane, but equally fascinating. Solar storms affect both comet behavior and Earth's technological systems through completely independent mechanisms. Comets respond to enhanced particle density and magnetic field variations in space. Earth's infrastructure responds to the same particle streams when they interact with our planet's magnetosphere. The correlation exists because both phenomena share a common solar cause, not because comets somehow influence terrestrial systems. This distinction becomes crucial when 3i Atlas enters the discussion. If satellite systems experience failures or power grids suffer disruptions during the interstellar visitor's passage, solar activity provides a far more plausible explanation than direct influence from a small, distant comet. The temptation to connect dramatic timing with exotic causation must be resisted in favor of established physical mechanisms. Government agencies responsible for space weather monitoring have developed sophisticated warning systems that track solar storms from their origin in solar flares through their propagation across interplanetary space to their impact on Earth's magnetosphere. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center issues forecasts and warnings with the same urgency applied to terrestrial severe weather events. These monitoring systems allow precise correlation between documented space weather events and any technological problems that might coincide with unusual comet activity. If infrastructure failures occur during periods of documented geomagnetic storms, solar causes become far more likely than mysterious comet influences. The enhanced solar activity of 2025 guarantees frequent opportunities for such correlations. Solar maximum conditions produce geomagnetic storms several times per month, creating numerous chances for coincidental timing between infrastructure problems and comet observations. The statistical expectation is that some correlations will occur purely by chance, regardless of any genuine causal relationships. Amateur radio operators provide an additional monitoring resource that often detects space weather effects before official systems issue warnings. Radio wave propagation through Earth's ionosphere becomes dramatically altered during geomagnetic storms, creating communication blackouts or unusual skip patterns that experienced operators recognize immediately. This distributed sensing network offers real-time feedback about space weather conditions that can help distinguish between solar-driven phenomena and potentially anomalous events that might indicate other influences. If 3I Atlas somehow affects Earth's electromagnetic environment, those effects should be detectable through multiple independent monitoring systems. The investigation framework requires constant vigilance against the attribution errors that arise when multiple dramatic events occur simultaneously. Human psychology strongly favors causal explanations for temporal correlations, particularly when the timing seems meaningful or purposeful. The more unusual the individual events, the more compelling their coincidence appears. But statistical analysis reveals that apparent clusters occur regularly in truly random distributions. Flip a coin long enough, and you'll eventually see sequences that seem impossible, but are mathematically inevitable. The same principle applies to correlations between space weather events, comet activity, and technological failures. The challenge lies in developing objective criteria for distinguishing between meaningful correlations and the kind of clustering that emerges randomly from complex systems. This requires establishing baseline expectations for how frequently various types of events should coincide purely by chance, then testing observed correlations against those statistical predictions. Professional space weather researchers develop sophisticated tools for addressing these challenges. Superposed epoch analysis, cross-correlation functions, and other statistical techniques can quantify the strength of relationships between different types of events, while accounting for the multiple comparison problems that arise when testing many potential correlations simultaneously. These analytical methods provide frameworks for evaluating claims about connections between 3I Atlas and terrestrial phenomena, without succumbing to the pattern-seeking biases that make coincidences appear more meaningful than they actually are. The standards for evidence must remain appropriately high to avoid false alarms while remaining sensitive enough to detect genuine signals if they exist. The global scope of modern technological infrastructure creates numerous opportunities for apparent correlations between celestial events and system failures. With millions of satellites, billions of electronic devices, and countless transmission systems operating continuously, some failures occur every day for purely random reasons. During periods of high comet activity or unusual solar behavior, these routine failures gain enhanced attention and possible misattribution. A power outage that would normally be attributed to equipment aging or maintenance problems might be blamed on exotic comet influences if it occurs during a period of heightened astronomical interest. Education and clear communication become essential tools for preventing such misattribution. The more people understand about the genuine mechanisms by which space weather affects terrestrial systems, the less likely they become to invoke exotic explanations for phenomena that conventional physics explains adequately. This educational component extends to our investigation of potential connections between 3I Atlas and the 7-comet swarm. By maintaining clear separation between established cause and effect relationships and speculative possibilities, we can explore exotic hypotheses without promoting unfounded theories as factual conclusions. The technological sophistication of modern civilization creates both opportunities and challenges for detecting subtle influences that might operate below the threshold of conventional space weather effects. Our increased sensitivity to electromagnetic phenomena might allow detection of weak signals that previous generations couldn't measure, but it also creates more chances for false correlations and misattributed causation. As we prepare to examine how human psychology and cultural narratives shape our interpretation of celestial events, remember that the universe operates according to physical laws that remain constant regardless of our hopes for dramatic discoveries. Earth's response to space weather follows well-understood mechanisms that don't require exotic explanations. Even during periods of unusual comet activity, the echoes of solar storms reverberate through our technological systems with predictable effects that can be measured, analyzed, and attributed to their genuine sources. But within the noise of normal space weather variability, subtle signals might await detection by instruments sensitive enough to distinguish between correlation and causation. Our investigation continues, grounded in established physics, but alert to possibilities that might challenge our current understanding of how celestial and terrestrial phenomena interact across the vast scales of space and time. Throughout human history, bright comets have served as cosmic messengers that cultures interpreted according to their deepest fears and highest aspirations. The arrival of multiple comets simultaneously taps into psychological patterns that have influenced human behavior for millennia, transforming objective astronomical events into subjective narratives about fate, change, and cosmic significance. Ancient Chinese astronomers maintained meticulous records of comet appearances, correlating celestial events with dynastic changes, natural disasters, and social upheavals. The Han Dynasty's historical records describe comets as broom stars that sweep away old orders to make way for new ones, a metaphor that reveals how civilizations have always sought meaning in cosmic timing. Medieval European chroniclers interpreted comet appearances as divine warnings about impending disasters or momentous changes. The Great Comet of 10,066, which appeared shortly before the Norman conquest of England, became forever linked with the fall of Saxon rule and the transformation of English society. Whether the comet actually influenced events or simply provided convenient symbolism remains debatable, but the correlation embedded itself permanently in historical memory. The 1758 return of Halley's Comet coincided with the 7 Years' War, a global conflict that reshaped political boundaries across 3 continents. Colonial American observers saw the comet as an omen of independence from British rule, while European astronomers celebrated it as confirmation of Newton's gravitational theories. The same celestial event supported completely different narratives depending on cultural context and political aspirations. These historical examples illustrate how human minds naturally link clustered unusual events into coherent stories that feel more meaningful than random coincidence. When multiple dramatic phenomena occur simultaneously, whether comets, wars, plagues, or social upheavals, we instinctively search for underlying connections rather than accepting independent causation. This pattern-seeking tendency becomes particularly pronounced during periods of social stress or uncertainty. When populations actively seek signs about future directions, the 2025 comet swarm arrives during an era of rapid technological change, climate concerns, and geopolitical tensions that create fertile ground for interpreting celestial events as harbingers of transformation. Modern media ecosystems amplify these ancient psychological patterns through mechanisms that would astonish medieval chroniclers. Social media algorithms prioritize engaging content over factual accuracy, ensuring that dramatic comet videos and speculative theories spread faster than careful astronomical explanations. The same neural pathways that once helped humans detect genuine patterns in natural environments now respond to digital stimuli designed to capture and hold attention. Video editing software allows amateur content creators to produce compelling narratives that combine real comet imagery with suggestive music, dramatic narration, and carefully selected visual effects. These productions can achieve professional production values while promoting theories that would never survive peer review in scientific journals. The democratization of content creation means that anyone with internet access can contribute to evolving narratives about celestial events. Multiple independent creators often converge on similar interpretations, without coordinating their efforts, creating the appearance of widespread consensus around ideas that might lack factual foundation. This distributed storytelling process can rapidly transform simple observations, 7 comets arriving in 2025, into elaborate narratives about cosmic significance, alien visitation, or impending doom. Each retelling adds new details, connections, and interpretations that gradually diverge from verifiable facts toward pure speculation. The presence of 3i Atlas in this narrative environment creates particularly fertile ground for creative interpretation. An interstellar visitor arriving during our most unusual comet year provides exactly the kind of mysterious timing that human brains interpret as purposeful rather than coincidental. The story practically writes itself: alien probe coordinates with comet swarm to deliver message or warning to Earth. The narrative satisfies multiple psychological needs simultaneously. It provides explanation for unusual timing, assigns agency to apparently random events, and positions human observers as witnesses to historically significant developments. Professional astronomy faces increasing challenges in competing with these compelling narratives for public attention. Careful explanations of orbital mechanics and statistical probability cannot match the emotional appeal of stories that transform observers into participants in cosmic drama. Scientific uncertainty, presented honestly as ranges of possibilities rather than definitive conclusions, sounds less authoritative than confident assertions about hidden meanings. The responsibility for maintaining factual accuracy in this environment requires constant vigilance against the temptation to oversell scientific conclusions or understate genuine uncertainties. When we acknowledge that some correlations exceed statistical expectations while emphasizing that correlation doesn't prove causation, we risk losing audience attention to sources that offer more definitive answers. Yet this challenge also presents opportunities for science education that traditional astronomy outreach rarely achieves. The high level of public interest in our seven-comet investigation creates teachable moments about hypothesis testing, statistical analysis, and the distinction between evidence and interpretation. By maintaining transparent separation between established facts and speculative possibilities, we can model the scientific process while exploring ideas that push against conventional boundaries. The investigation becomes an exercise in critical thinking that demonstrates how extraordinary claims require extraordinary evidence without dismissing unusual observations simply because they seem improbable. The cultural lens through which people interpret our findings inevitably shapes their conclusions regardless of the evidence we present. Viewers seeking confirmation of alien visitation will interpret ambiguous results as supportive of their preferred theories. Skeptics committed to conventional explanations will dismiss even strong correlations as inadequate proof of exotic mechanisms. This polarization reflects deeper questions about epistemology, how we decide what constitutes reliable knowledge and sufficient evidence for accepting unusual claims. Different communities apply different standards based on their experiences, training, and philosophical commitments about the nature of reality. The scientific approach requires provisional acceptance of conclusions based on available evidence, while remaining open to revision as new data becomes available. This intellectual humility can appear weak compared to the confident certainty that characterizes both true believers and dedicated skeptics. Yet this flexibility represents science's greatest strength in distinguishing between genuine discoveries and wishful thinking. The history of astronomy includes numerous examples of initially ridiculous ideas that eventually proved correct through accumulating evidence, as well as compelling theories that ultimately failed when tested against more precise observations. Our investigation of potential connections between 3I Atlas and the seven-comet swarm must navigate these cultural and psychological currents without being captured by them. The evidence will speak for itself, but only if we maintain appropriate standards for interpretation, while remaining sensitive to signals that might challenge conventional assumptions. As we prepare to examine the most sensational aspects of public speculation about our comet investigation, remember that human fascination with cosmic mysteries reflects legitimate wonder about our place in the universe. The challenge lies in channeling that wonder toward questions that can be answered through careful observation and analysis. The ancient pattern seekers who saw omens in comet tails weren't entirely wrong. Celestial events do provide information about cosmic processes that affect human civilization, but the connections operate through physics rather than magic, and understanding them requires tools more sophisticated than intuition and storytelling. The harbingers have arrived, carrying messages written in the universal language of orbital mechanics and spectroscopy. But first we need to decode the more colorful human interpretations that inevitably surround such mysterious timing. The most sensational interpretation of our seven-comet swarm requires courage to articulate clearly 3I Atlas is an artificial probe from another civilization, and the traditional comets represent a coordinated fleet responding to its arrival. This hypothesis pushes far beyond conventional astronomy into speculative territory that demands extraordinary evidence, but the implications are so profound that dismissal without investigation would be equally unscientific. Let's examine what genuine artificial origin would look like through the lens of established physics rather than science fiction fantasy. An engineered object traveling between stellar systems would need to solve problems that challenge our current technology: propulsion across interstellar distances, navigation with precision spanning millions of years, and communication across light years of space. The energy requirements alone stagger human comprehension. Accelerating even a small probe to the velocities necessary for interstellar travel demands power sources that dwarf current human capabilities. Nuclear pulse propulsion, antimatter engines, or exotic physics we haven't discovered yet would be required to achieve the speeds that bring objects between stellar systems within reasonable timeframes. Navigation presents equally daunting challenges. 3i Atlas's trajectory demonstrates remarkable precision in targeting our solar system from launch points potentially hundreds of light-years distant. Such accuracy requires detailed knowledge of stellar positions and motions across geological timescales, suggesting observational capabilities and computational resources far exceeding our own. But these engineering challenges, while impressive, don't violate known physics. Advanced civilizations might reasonably develop technologies that solve interstellar travel problems through brute force application of physical principles we understand but cannot yet implement. The question isn't whether such probes are theoretically possible, but whether 3i Atlas exhibits characteristics that distinguish artificial from natural objects. Spectroscopic analysis provides our most direct tool for detecting artificial composition. Natural comets display emission lines characteristic of water, ice, carbon compounds, and simple molecules that form readily in the cold outer regions of stellar systems. Artificial probes might contain manufactured materials, refined metals, exotic alloys, or synthetic compounds that don't occur naturally in comet-forming environments. The spectrum of 3i Atlas, when analyzed with sufficient detail, should reveal whether its composition matches expectations for natural comet materials or includes signatures that suggest artificial origin. Any detection of clearly manufactured substances would constitute compelling evidence for engineered construction, while purely natural spectra would argue strongly against the artificial origin hypothesis. Behavioral analysis offers another avenue for detecting artificial characteristics. Natural comets follow ballistic trajectories determined entirely by gravitational forces and occasional outgassing that creates small but measurable thrust effects. Artificial probes might demonstrate course corrections, attitude changes, or other maneuvers that indicate active control rather than passive response to environmental forces. The orbital elements of 3i Atlas show no evidence of non-gravitational perturbations beyond what natural outgassing could produce. Its trajectory appears consistent with a passive object following physics rather than engineering. However, subtle control inputs might remain below current detection thresholds, particularly if designed to mimic natural comet behavior. Communication signatures represent perhaps the most definitive test for artificial origin. Operating probes would likely maintain contact with their creators through radio transmissions, laser pulses, or other electromagnetic signals that could be detected by terrestrial radio telescopes. The search for extraterrestrial intelligence community has protocols for analyzing such signals and distinguishing artificial from natural radio sources. Systematic monitoring of 3i Atlas across multiple frequency bands has detected no obvious artificial signals, though the analysis continues as the object approaches closer to Earth. The absence of detectable transmissions doesn't eliminate artificial origin possibilities, since advanced civilizations might use communication methods we haven't conceived or frequencies we're not monitoring. The coordination hypothesis extends artificial origin speculation to our 7 traditional comets, suggesting they represent some form of engineered fleet responding to 3i Atlas's arrival. This scenario requires even more extraordinary assumptions about advanced technology and strategic planning across interstellar distances. Each member of our comet swarm would need independent propulsion and navigation capabilities, sophisticated enough to coordinate arrivals within narrow time windows. The logistics of such coordination boggle human imagination. 7 different objects launch from potentially different locations at different times, all arriving within months of each other after journeys spanning millennia. Yet the orbital characteristics of our 7 traditional comets show clear signatures of solar system origin. Their compositions match expected patterns for objects formed in our outer system. Their discovery histories trace back to well-documented survey programs that have been tracking these objects for years or decades. Their trajectories show no evidence of artificial course corrections or coordinated maneuvers. If these objects represent artificial constructs, they would need to be remarkably sophisticated camouflage operations designed to perfectly mimic natural solar system comets. Such deception would require detailed knowledge of our astronomical capabilities and expectations, suggesting surveillance and analysis capabilities that exceed their apparent technological demonstrations. The timing correlation between 3i Atlas and our comet swarm remains the strongest argument for some form of coordination. Even if the mechanism remains unclear, Statistical analysis of comet arrival patterns could reveal whether 2025 represents a genuinely unusual clustering that exceeds reasonable expectations for random distribution. But timing alone provides weak evidence for artificial coordination when considered against the backdrop of increasing survey capabilities and natural variation in comet discovery rates. The proliferation of automated sky surveys dramatically increases the probability of detecting objects that might have remained undiscovered in previous decades. The psychological appeal of alien explanations reflects deeper human needs to find purpose and intelligence behind apparently random events. When faced with unusual coincidences, we naturally prefer explanations that invoke agency rather than accepting that chance produces patterns that feel meaningful but aren't. The alien hypothesis also satisfies contemporary anxieties about humanity's cosmic isolation and technological limitations. If advanced civilizations are visiting our solar system, it suggests we're not alone in the universe and that technological development beyond our current capabilities is possible. However, extraordinary claims require extraordinary evidence, and the alien hypothesis clearly qualifies as extraordinary. The burden of proof lies with proponents to demonstrate artificial characteristics that survive skeptical analysis, rather than requiring skeptics to prove negative propositions about non-detection of subtle signals. Current observational data provides insufficient evidence to support artificial origin conclusions for either 3I Atlas or any members of our comet swarm. While we cannot definitively rule out sophisticated camouflage operations that perfectly mimic natural objects, such scenarios require assumptions about alien capabilities and motivations that extend far beyond available evidence. The investigation remains ongoing as improved observations might reveal characteristics that current analysis has missed. Closer approaches will enable more detailed spectroscopic analysis, higher resolution imaging, and more sensitive searches for artificial signals or behavioral anomalies. Professional astronomy maintains appropriate skepticism about exotic explanations while continuing systematic observation and analysis that could detect genuine artificial characteristics if they exist. The scientific method provides frameworks for distinguishing between wishful thinking and legitimate discoveries when applied with appropriate rigor. The search for extraterrestrial intelligence represents one of the most profound questions facing human civilization. If evidence emerges that 3I Atlas or any associated objects exhibit genuine artificial characteristics, such discovery would transform our understanding of our place in the universe. But until such evidence meets the rigorous standards necessary to convince skeptical scientists, the alien hypothesis remains in the category of speculation rather than established fact. The wonder and possibility remain alive while acknowledging that current observations favor conventional explanations over exotic alternatives. As we examine even more dramatic scenarios that human imagination has constructed around our unusual comet year, remember that maintaining scientific rigor doesn't require abandoning curiosity about possibilities that challenge conventional assumptions. The universe has surprised us before with phenomena that initially seemed impossible. The darkest interpretation of our seven-comet convergence paints 2025 as a year of civilization-threatening catastrophe orchestrated by forces beyond human control. This doomsday narrative transforms celestial mechanics into cosmic warfare, turning ice and rock into weapons capable of ending human history. While such scenarios make compelling fiction, evaluating them requires honest assessment of actual risks versus psychological fears that attach to unusual astronomical events. Real impact hazards follow well-understood physics that allows precise calculation of collision probabilities and consequences. When asteroids or comets approach Earth on trajectories that might intersect our planet's orbital path, professional astronomers can predict encounter circumstances with mathematical certainty. The orbital mechanics that govern these calculations operate with clockwork precision, leaving no room for ambiguity about genuine collision risks. None of our 7 Comet cast members follows trajectories that pose any impact threat to Earth during their current approaches. Pan-STARRS, SWAN, Stereo, Atlas K1, Atlas G3, Lemon, and Nemawise all maintain safe distances measured in millions of kilometers. Their closest approaches place them far beyond the gravitational influence zones that could lead to catastrophic encounters. 3I Atlas follows a hyperbolic trajectory that carries it safely past all major solar system bodies. Its interstellar origin and high velocity relative to solar system objects actually reduce collision probabilities rather than enhancing them, since gravitational capture becomes impossible for objects moving at hyperbolic speeds. The absence of impact risk doesn't eliminate all potential hazards associated with enhanced comet activity. Space weather effects driven by solar maximum conditions can threaten technological infrastructure in ways that modern civilization struggles to accommodate. Electrical power grids, satellite communication systems, and navigation networks all face vulnerabilities during periods of intense solar particle bombardment. But these technological risks stem from solar activity rather than comet behavior. Our star's 11-year magnetic cycle reaches maximum intensity in 2025 independent of any comet arrivals. The timing correlation between active comets and active solar conditions reflects shared response to solar system dynamics rather than causation flowing from comets to solar behavior. The quantification of risk requires statistical analysis that separates genuine threats from the kind of coincidental clustering that feels meaningful to pattern-seeking human brains. When multiple low-probability events occur simultaneously, intuitive risk assessment often overestimates the likelihood that something coordinated and threatening is occurring. Professional risk analysis employs mathematical frameworks that account for the multiple comparison problems inherent in evaluating numerous potential correlations simultaneously. When testing many possible relationships between different types of events, some apparent patterns will emerge purely by chance, regardless of any genuine causal mechanisms. The doomsday scenario gains psychological traction by bundling our 7-comet swarm plus 3i atlas into a single threatening entity rather than treating each object as an independent phenomenon. This bundling transforms 7 separate low-risk events into one apparently high-risk situation that seems to demand immediate concern and preparation. Yet orbital mechanics doesn't recognize such artificial bundling. Each object follows its own trajectory, determined by gravitational forces that operate independently for each comet. The apparent coordination exists in human perception rather than physical reality, created by observation timing rather than genuine interaction between objects. Historical precedent provides perspective on how unusual astronomical events relate to terrestrial disasters. Bright comets have appeared during periods of war, plague, famine, and social upheaval throughout recorded history. But careful analysis reveals no statistical correlation between comet appearances and increased rates of human catastrophe. The perception of correlation arises because dramatic celestial events receive enhanced attention during periods when populations are already stressed by terrestrial problems. Chronicles written during difficult times naturally emphasize any unusual phenomena that might seem relevant to ongoing struggles, while similar astronomical events that occur during peaceful periods attract less historical notice. Modern civilization faces legitimate existential risks that deserve serious attention. Nuclear warfare, climate change, pandemic diseases, and technological disruption all pose genuine threats to human welfare. These risks operate through well-understood mechanisms that can be analyzed, modeled, and potentially mitigated through appropriate policies and preparations. The doomsday comet scenario distracts attention from these real risks by focusing concern on phenomena that pose minimal actual threat to human civilization. Misallocating limited attention and resources toward imaginary threats reduces our collective ability to address genuine challenges that require sustained effort and coordination. Sensational claims about cosmic threats must meet higher evidentiary standards than casual speculation about unusual coincidences. When someone suggests that our comet swarm poses civilization-level risks, we need specific mechanisms, quantified probabilities, and independently verifiable evidence rather than vague assertions about suspicious timing. The scientific method provides frameworks for evaluating such claims objectively. Hypothesis testing, statistical analysis, and peer review help distinguish between legitimate concerns based on evidence and unfounded fears that reflect psychological biases rather than physical threats. Emergency preparedness agencies maintain sophisticated monitoring systems that track genuine space weather hazards and assess their potential impacts on critical infrastructure. These systems would detect and warn about any real threats posed by enhanced comet activity or solar maximum conditions long before such threats materialized. The absence of official warnings from agencies responsible for space weather monitoring argues strongly against scenarios that predict imminent technological collapse triggered by comet-related phenomena. Professional risk assessors with access to the most complete observational data see no evidence of extraordinary threats requiring emergency response. Public education about actual space weather risks helps maintain appropriate perspective about the difference between dramatic spectacle and genuine hazard. Solar storms can indeed threaten technological systems, but the threats operate through well-understood mechanisms that can be predicted, monitored, and mitigated through engineering solutions. The enhanced comet activity of 2025 will provide spectacular observing opportunities and valuable scientific data about solar system dynamics. These benefits far outweigh any realistic risks associated with the observations themselves. The real hazard lies in allowing unfounded fears to overshadow legitimate scientific curiosity and educational opportunities. Responsible science communication requires honest acknowledgement of uncertainties while maintaining appropriate perspective about the scale of actual risks. When we admit that some aspects of our comet investigation remain unexplained, we must also emphasize that unexplained doesn't mean threatening. The universe regularly produces phenomena that challenge current understanding without posing immediate dangers to human civilization. Scientific progress depends on investigating such phenomena systematically, while avoiding premature conclusions based on incomplete evidence or psychological biases. As we prepare to examine the most elaborate conspiracy theories that human creativity has constructed around our unusual comet year, remember that extraordinary claims about cosmic threats require extraordinary evidence to justify serious consideration. Fear-based speculation serves no constructive purpose when divorced from rigorous analysis of actual probabilities and mechanisms. The doomsday scenario reveals more about human psychology than about cosmic physics. Our pattern-seeking brains naturally interpret clustered unusual events as coordinated threats rather than statistical coincidences, particularly during periods of social stress when populations actively seek explanations for their anxieties. But the universe operates according to physical laws that remain indifferent to human fears and expectations. Comets follow gravitational trajectories that can be calculated precisely. Solar activity follows magnetic cycles that can be predicted statistically, and space weather effects follow electromagnetic principles that can be measured and modeled. The cosmic clockwork continues its precise operation regardless of the dramatic narratives we construct around its most visible manifestations. Understanding that clockwork provides both practical benefits and profound satisfaction that transcends the temporary thrills of doomsday speculation. The most elaborate conspiracy theory surrounding our seven-comet phenomenon suggests that we're witnessing the initial phase of an extraterrestrial invasion disguised as natural astronomical events. In this scenario, 3I Atlas serves as a command vessel, coordinating a fleet of objects that masquerade as traditional comets while conducting reconnaissance and preparing for eventual occupation of our solar system. This invasion hypothesis requires technological sophistication that staggers human imagination. Each alleged probe would need camouflage capabilities, advanced enough to perfectly mimic the spectroscopic signatures, outgassing behavior, and orbital characteristics of natural solar system comets. Such deception would demand intimate knowledge of our astronomical capabilities and detailed understanding of how genuine comets behave under solar heating. Consider the engineering challenges involved in creating artificial objects that could fool our most sophisticated instruments. Modern spectroscopy can identify molecular species with extraordinary precision, distinguishing between isotopic ratios that reveal formation environments and chemical processes. Any artificial probe would need to carry materials that exactly match the composition expected for objects formed in our outer solar system billions of years ago. The outgassing behavior that creates comet tails presents equally daunting camouflage requirements. Natural comets develop their characteristic appearance through sublimation of volatile materials under solar heating, a process that depends on internal structure, composition, and thermal properties developed over geological timescales. Artificial mimicry would require sophisticated engineering to replicate these behaviors convincingly. Light curves, the patterns of brightness variation that characterize comet behavior, provide another avenue for detecting artificial origin. Natural comets typically show smooth brightness changes punctuated by occasional outbursts when fresh volatile materials become exposed. The rotation periods revealed by brightness variations reflect the natural tumbling motion of irregularly shaped objects under minimal gravitational binding. If our 7 traditional comets represented artificial constructs, their light curves should eventually reveal characteristics that distinguish engineered from natural behavior, artificially controlled rotation, precisely timed brightness variations, or other signatures of active attitude control would become apparent through sustained photometric monitoring. The orbital characteristics of disguised probes present the most fundamental camouflage challenge. Each member of our comet swarm follows a trajectory that can be traced backward through millions of years of gravitational evolution. These orbital histories carry the signatures of their formation regions, planetary encounters, and gravitational perturbations that shaped their current paths. Creating artificial objects with orbital characteristics indistinguishable from natural solar system, natives would require launching them from appropriate distances and directions, while ensuring their trajectories match expectations for objects formed in specific regions of the outer solar system. The logistics of such an operation across interstellar distances and geological timescales challenge comprehension. Moreover, the discovery histories of our 7 comets trace back to well-documented survey programs that have been tracking these objects for years or decades. NEY's, Lemon, and the Atlas surveys maintain comprehensive archives that record the circumstances of each discovery and the subsequent orbital determinations that establish their predicted arrival times. If these objects represent recently arrived artificial constructs rather than long-period comets completing natural orbits, their sudden appearance in survey data would have triggered immediate attention from astronomers experienced in orbital analysis. The absence of such alerts argues strongly against scenarios involving recently deployed artificial objects masquerading as traditional comets. The communication aspects of a coordinated invasion fleet present additional opportunities for detection. Maintaining coordination among 7 distributed objects, plus a command vessel, would require frequent data exchange through radio transmissions, laser communications, or other electromagnetic signals that terrestrial monitoring systems could intercept. The search for extraterrestrial intelligence community operates sophisticated radio telescopes that continuously monitor large portions of the sky for artificial signals. Project Breakthrough, Listen, the Arecibo Observatory legacy programs, and numerous other initiatives maintain systematic searches for exactly the kind of artificial signals that coordination between invasion fleet elements would require. The absence of detected artificial signals associated with our comet swarm doesn't eliminate all communication possibilities, since advanced civilizations might employ methods beyond current human detection capabilities. However, the coordination requirements for maintaining fleet operations across solar system distances would likely necessitate signal strengths and repetition patterns that contemporary instruments could detect. The strategic logic of disguised invasion scenarios faces fundamental questions about cost-effectiveness and risk management. Why would advanced civilizations capable of interstellar travel choose such elaborate deception when direct approach would achieve reconnaissance objectives more efficiently? What strategic advantage does camouflage provide when the target civilization lacks defensive capabilities against interstellar-capable technology? The resource investment required for creating and deploying 7 sophisticated camouflage probes, plus a command vessel, would exceed the gross economic output of human civilization by orders of magnitude. Advanced civilizations capable of such investments would possess technological advantages so overwhelming that deception becomes strategically irrelevant. Furthermore, the invasion scenario assumes hostile intent without evidence of threatening behavior from any detected objects. None of our comet swarm members demonstrate capabilities beyond what natural objects should possess. 3i Atlas follows a departure trajectory that will carry it permanently out of the solar system, hardly consistent with establishing permanent presence for invasion purposes. The psychological appeal of invasion scenarios reflects contemporary anxieties about technological disruption, resource competition, and loss of human agency in the face of superior capabilities. These fears attach readily to unusual astronomical phenomena that suggest forces operating beyond human control or understanding. But speculation about extraterrestrial intentions, however creative, cannot substitute for empirical evidence about the nature and behavior of observed objects. The invasion hypothesis requires positive evidence of artificial characteristics, coordinated behavior, or threatening capabilities rather than relying on the absence of proof that objects are entirely natural. Current observational data provides no support for artificial origin conclusions regarding any member of our comet swarm. Spectroscopic analysis reveals compositions consistent with natural formation in solar system environments. Orbital characteristics match expectations for objects following gravitational evolution over millions of years. Behavioral patterns show no evidence of active control or coordination beyond statistical coincidence. The burden of proof lies with proponents of extraordinary claims to demonstrate artificial characteristics that survive rigorous skeptical analysis. Absence of such evidence doesn't prove that invasion scenarios are impossible, but it does argue that current observations favor conventional astronomical explanations over exotic alternatives. Professional astronomy maintains systematic monitoring of all unusual objects precisely to detect any characteristics that might indicate artificial origin. The community takes such possibilities seriously enough to maintain established protocols for evaluating potential extraterrestrial artifacts, while applying appropriate evidentiary standards to distinguish between speculation and legitimate discovery. The investigation continues as closer approaches enable more detailed analysis of object characteristics and behavior. If genuine artificial signatures exist, they should become more apparent as observational capabilities improve and additional data accumulates over time. Science fiction scenarios serve valuable functions in exploring possibilities and preparing conceptual frameworks for unexpected discoveries. But entertainment value doesn't justify promoting speculative scenarios as factual conclusions when available evidence fails to support extraordinary claims. The universe provides enough genuine mysteries without requiring us to invent additional puzzles based on wishful thinking or fear-driven speculation. Our 7-comet swarm represents a legitimate statistical anomaly worthy of investigation, but that investigation should follow evidence rather than predetermined conclusions about invasion fleets and cosmic conspiracies. As we prepare to synthesize our investigation's findings and conclusions, remember that maintaining scientific rigor doesn't require abandoning wonder about cosmic possibilities. The tools of empirical investigation that help distinguish between reality and fantasy also provide the means for recognizing genuine discoveries when extraordinary evidence finally appears. The cosmos may yet surprise us with phenomena that challenge conventional assumptions, but such surprises will arrive through careful observation and analysis, rather than speculative leaps beyond available evidence. After months of investigation, tracking orbital mechanics, analyzing statistical probabilities, and examining every conceivable connection between 3I Atlas and our 7-comet parade, the evidence points toward a conclusion that's simultaneously reassuring and remarkable. We're witnessing an extraordinary natural phenomenon rather than evidence of exotic coordination or extraterrestrial intervention. The 7-comet swarm of 2025 represents genuine statistical clustering that captures attention precisely because such concentrations occur rarely enough to feel meaningful. Pan-STARRS, SWAN, Stereo, Atlas K1, Atlas G3, Lemon, and Neowise are following independent orbital paths determined by gravitational forces that began shaping their trajectories millions of years ago, long before human civilization existed to witness their eventual convergence. Yet dismissing this convergence as mere coincidence understates the profound beauty and scientific value of what we're experiencing. The universe has arranged a celestial festival that provides unprecedented opportunities for comparative comet studies, public astronomy education, and deeper understanding of outer solar system dynamics. The timing may be natural, but the scientific and cultural impact remains extraordinary. 3I Atlas adds an additional layer of wonder as our solar system's first well-documented interstellar visitor that exhibits clear comet-like behavior. This object carries ice and dust forged around another star, seasoned by millions of years of interstellar travel, now vaporizing under our sun's heat, to create tails that make alien chemistry visible to telescopes worldwide. The timing correlation between our interstellar visitor and the most active comet year in recent memory continues to intrigue researchers. Even though current evidence suggests coincidence rather than causation, sometimes the universe arranges meaningful feeling patterns through purely natural processes, reminding us that coincidence and significance can coexist without requiring mysterious explanations. The investigation has revealed no orbital relationships, behavioral anomalies, or timing correlations that exceed what statistical analysis predicts for independent objects influenced only by conventional gravitational and solar heating effects. Each comet tells its own story of formation in the outer solar system, gravitational perturbations that initiated its current orbit, and response to increasing solar radiation as it approaches perihelion. This conclusion doesn't diminish the scientific excitement surrounding 2025's unusual celestial activity. Multiple bright comets provide comparative opportunities that rarely occur within single observing seasons. Researchers can study how different compositions, sizes, and orbital geometries respond to similar solar heating conditions, advancing our understanding of comet physics in ways that isolated observations cannot achieve. The enhanced solar activity that accompanies solar maximum conditions will amplify the visual spectacle of our comet parade while providing natural experiments in space weather physics. The same coronal mass ejections that threaten technological infrastructure create the dramatic tail disconnections and plasma instabilities that make comet photography so compelling during active solar periods. Amateur astronomers worldwide are documenting this celestial festival with unprecedented detail, creating photographic archives that will inform scientific research for decades. The democratization of high-quality astronomical imaging means that hundreds of observers contribute data that supplements professional monitoring programs, multiplying our observational capabilities beyond what any single institution could achieve. The public engagement generated by our 7-comet investigation demonstrates how unusual astronomical events can catalyze interest in space science and critical thinking skills. The process of evaluating extraordinary claims against available evidence provides educational opportunities that traditional astronomy outreach rarely achieves, showing how the scientific method distinguishes between speculation and established fact. The absence of exotic connections doesn't eliminate all possibilities for future discoveries. Continued monitoring might reveal subtle correlations that current analysis has missed, or closer approaches might enable detection of characteristics that remain below present observational thresholds. Science progresses through incremental improvements in measurement precision and analytical techniques that occasionally reveal previously hidden phenomena. The statistical clustering that characterizes 2025 could also provide insights into long-term solar system dynamics that operate on timescales exceeding human historical records. If similar clustering occurred in the past or occurs in predictable patterns, it might reflect gravitational resonances, solar cycle effects, or other periodic influences that shape comet arrival timing over astronomical timescales. Professional astronomy will continue systematic observation and analysis of all unusual objects, maintaining vigilance for characteristics that might indicate artificial origin or exotic physical processes. The community takes such possibilities seriously, while applying appropriate evidentiary standards to distinguish between legitimate anomalies and statistical fluctuations in complex datasets. The broader implications of our investigation extend beyond the specific question of connections between 3I Atlas and traditional solar system comets. The process demonstrates how rigorous scientific inquiry can address exotic hypotheses without becoming captured by the speculation that such hypotheses generate in popular culture. Maintaining this balance between curiosity and skepticism becomes increasingly important as social media algorithms amplify sensational claims faster than careful analysis can evaluate them. The scientific community bears responsibility for providing accurate information while acknowledging uncertainties honestly rather than competing with entertainment-focused content through exaggerated claims or premature conclusions. The 2025 Comet experience also illustrates how pattern-seeking human psychology can transform objective astronomical events into subjective narratives about cosmic significance. This transformation isn't necessarily problematic. Finding meaning and wonder in celestial phenomena has inspired human cultures throughout history, but it requires conscious separation between factual observations and interpretive frameworks. The tools of modern astronomy provide unprecedented capabilities for distinguishing between genuine anomalies and apparent patterns that emerge from normal statistical variation. These same tools reveal universe-scale phenomena that exceed human imagination without requiring exotic explanations, demonstrating that reality often surpasses the creativity of speculation. As our investigation concludes, we're left with a cosmos that remains simultaneously more comprehensible and more mysterious than popular narratives suggest. The universe operates according to physical laws that can be discovered and understood through careful observation, yet those same laws produce phenomena that challenge intuition and inspire continued exploration. The message of the 2025 swarm may ultimately be that the universe provides enough genuine wonder without requiring us to invent additional mysteries. 7 independent comets converging through natural processes, while an interstellar visitor makes its first and only passage through our solar system, represents a cosmic coincidence worth celebrating for its own remarkable timing. The educational value of this experience extends far beyond astronomy. to critical thinking skills that apply across all domains of human knowledge, learning to distinguish between correlation and causation, to evaluate claims against appropriate evidence standards, and to maintain wonder while demanding rigor, provides intellectual tools that serve society well beyond the specific context of comet investigations. Future observers may look back on 2025 as a watershed year when improved survey capabilities and social media attention combined to transform routine astronomical discoveries into cultural phenomena that engaged millions of people worldwide in discussions about evidence, probability, and the nature of scientific knowledge. The swarm's ultimate message may be that human curiosity and analytical capability, rather than exotic cosmic coordination, represent the most remarkable aspects of this entire experience. We've developed tools sophisticated enough to detect interstellar visitors, calculate orbital elements with extraordinary precision, and evaluate extraordinary claims through rigorous statistical analysis. This technological and intellectual achievement deserves recognition alongside any spectacular celestial phenomena we're privileged to witness. The universe may not be sending us messages through coordinated comet arrivals, but it continues providing opportunities for discovery that reward careful observation with deeper understanding of our cosmic environment. The investigation concludes where it began, with wonder at unusual timing, respect for rigorous analysis, and appreciation for a universe that supplies enough authentic mystery to occupy human curiosity for millennia to come. Hypothesis tested, evidence evaluated, wonder preserved intact for future investigations that await beyond our current observational horizons. But our investigation isn't complete without examining the deeper implications of what we've discovered and what we haven't. The absence of exotic coordination doesn't diminish the profound questions that our seven-comet swarm raises about the nature of coincidence, the limits of statistical analysis, and the human tendency to find patterns in cosmic chaos. The mathematical framework we've used to evaluate potential connections between 3I Atlas and our traditional comets provides a template for investigating similar phenomena in the future. As automated sky surveys become more sensitive and comprehensive, we'll inevitably encounter other statistical clusters that challenge our understanding of randomness and causation. The Pan-STAR survey alone discovers hundreds of new asteroids and comets each year, creating a vast database of orbital elements that future researchers will mine for patterns we can't yet imagine. The Legacy Survey of Space and Time, scheduled to begin operations later this decade, will increase the discovery rate by orders of magnitude. This exponential growth in observational capability means that statistically unusual events like our 2025 comet swarm will become more common, not because the universe is becoming more coordinated, but because we're sampling larger portions of the cosmic population. Each new survey reveals objects that were always there, waiting for sufficiently sensitive instruments to announce their presence. The challenge for future astronomers will be developing analytical tools sophisticated enough to distinguish between genuine anomalies and the kind of apparent clustering that emerges naturally from large datasets. Machine learning algorithms already assist in asteroid and comet classification, but pattern recognition in temporal sequences requires more nuanced approaches. Consider the implications of discovering 10 comets arriving simultaneously in 2035, or 15 in 2045. At what point does statistical clustering become so extreme that conventional explanations seem inadequate? The mathematics of probability provides clear guidelines, but the psychological impact of witnessing multiple rare events simultaneously. The 2025 experience teaches us that extraordinary claims require extraordinary evidence, but it also demonstrates how easily extraordinary evidence can be misinterpreted when filtered through pattern-seeking human psychology. The same cognitive abilities that help us navigate complex environments can lead us astray when applied to phenomena that operate on scales beyond our intuitive understanding. Professional astronomy has developed institutional safeguards against premature conclusions about unusual observations. Peer review, independent verification, and statistical analysis all help prevent the kind of speculative overreach that transforms interesting coincidences into unfounded theories about alien intervention or cosmic conspiracies. But these safeguards work best when applied consistently across all levels of scientific communication. The challenge in our current media environment is maintaining factual accuracy while competing for public attention with sources that prioritize engagement over evidence. The democratization of content creation means that anyone with internet access can contribute to public discourse about astronomical discoveries. This democratic participation brings valuable perspectives and observational capabilities that supplement professional research, but it also creates opportunities for misinformation to spread faster than factual corrections. Educational institutions bear particular responsibility for teaching critical thinking skills that help students evaluate extraordinary claims against appropriate evidence standards. The ability to distinguish between correlation and causation, to understand statistical probability, and to recognize the difference between speculation and established fact serves society well beyond the specific context of astronomical investigations. The 2025 comet swarm provides an ideal case study for exploring these concepts because it combines genuine statistical unusualness with clear observational data that can be analyzed objectively. Students can examine the same evidence that professional astronomers use, apply statistical tests to evaluate potential correlations, and reach their own conclusions about whether exotic explanations are warranted. This hands-on approach to scientific reasoning builds intellectual confidence while demonstrating how the scientific method distinguishes between reliable knowledge and wishful thinking. The process reveals that science isn't about accepting authority figures' pronouncements, but about learning to evaluate evidence independently using tools that anyone can master. The technological infrastructure that enables modern astronomical discovery also provides unprecedented opportunities for citizen participation in scientific research. Amateur astronomers contribute crucial observations that supplement professional monitoring programs, particularly for time-variable phenomena like comet outbursts and brightness fluctuations. Coordinated observation campaigns for events like 3I Atlas's perihelion passage demonstrate how distributed networks of observers can achieve coverage that no single institution could match. This collaborative approach multiplies our scientific capabilities while engaging broader communities in the process of discovery. The psychological aspects of pattern recognition in astronomical observations deserve continued investigation because they affect both professional and amateur researchers. Understanding how human brains respond to unusual clustering helps us develop better analytical tools and communication strategies. Cognitive scientists have identified specific biases that influence how people interpret temporal coincidences. The availability heuristic makes recent or dramatic events seem more probable than they actually are. Confirmation bias leads us to notice evidence that supports preferred conclusions while ignoring contradictory data, and the clustering illusion makes random patterns appear more meaningful than they actually are. These biases don't disappear when people receive scientific training. They require conscious effort to recognize and counteract. The most rigorous astronomical research incorporates safeguards specifically designed to minimize the influence of unconscious pattern-seeking tendencies. Double-blind observation protocols prevent researchers from knowing which data might support their hypotheses until after analysis is complete. Statistical methods account for multiple comparison problems that arise when testing numerous potential correlations simultaneously. Independent replication ensures that apparent patterns survive scrutiny by different research groups using different instruments and techniques. The application of these rigorous standards to our comet investigation reveals no evidence for exotic coordination between 3I Atlas and the 7 traditional comets. Each object follows an independent trajectory determined by gravitational forces that began operating millions of years before human civilization existed to witness their convergence. Yet the absence of coordination doesn't eliminate the profound educational and scientific value of witnessing such convergence. The comparative opportunities provided by multiple bright comets in a single observing season advance our understanding of outer solar system dynamics in ways that isolated observations cannot achieve. Different comet compositions respond differently to solar heating, creating natural experiments in planetary formation processes. The variety of orbital inclinations and eccentricities represented in our swarm samples, different regions of the Oort cloud and Kuiper belt, providing insights into the structure and evolution of the outer solar system. The enhanced solar activity that accompanies 2025 solar maximum creates additional natural experiments in space weather physics. The same coronal mass ejections that threaten technological infrastructure provide opportunities to study how high-energy particle streams interact with comet atmospheres and tails. These interactions reveal fundamental physics that operates throughout the universe: the behavior of ionized gases in magnetic fields, the dynamics of radiation pressure on small particles, and the response of volatile materials to intense electromagnetic radiation. Understanding these processes in our local cosmic environment helps us interpret similar phenomena observed around other stars. The spectroscopic analysis of 3I Atlas provides unprecedented insights into chemical processes that occurred in another stellar system. Every emission line in its spectrum carries information about formation conditions that existed around a different star under potentially different physical laws or fundamental constants. Comparative studies of interstellar versus solar system materials might reveal subtle differences that illuminate how stellar environments affect planetary formation. The isotopic ratios preserved in 3I Atlas's ice and dust have remained unchanged since its formation, providing a direct sample of another world's ancient chemistry. These scientific opportunities justify the intensive observational campaigns that professional and amateur astronomers are conducting throughout 3I Atlas's passage. Every photon of light we collect from this object represents irreplaceable information about conditions beyond our solar system. The technological challenges of detecting and analyzing such faint signals from distant objects demonstrate how far astronomical instrumentation has advanced in recent decades. Modern CCD cameras can detect individual photons with extraordinary efficiency. Computerized tracking systems can follow moving objects across the sky with precision that was unimaginable a generation ago, and automated analysis software can extract spectroscopic data from observations that would have required weeks of manual effort using older techniques. This technological progress accelerates the pace of discovery while creating new opportunities for serendipitous observations. Automated sky surveys operate continuously, scanning vast areas of sky and alerting astronomers immediately when unusual objects appear. The discovery rate for near-Earth asteroids now exceeds 1,000 objects per year, compared to perhaps a dozen per year in the 1990s. Comet discoveries have increased proportionally, though the fraction that develop into naked-eye spectacles remains frustratingly small. This abundance of new discoveries creates both opportunities and challenges for astronomical research. The sheer volume of data requires automated analysis tools that can identify potentially interesting objects without human intervention. Machine learning algorithms excel at classification tasks, but they require careful training to avoid missing genuinely unusual phenomena. The balance between automated efficiency and human insight remains crucial for astronomical discovery. Computers excel at processing large volumes of routine data, but human pattern recognition often identifies subtle anomalies that escape algorithmic detection. The investigation of our 2025 comet swarm exemplifies this human-computer collaboration. Automated surveys discovered most of our 7 traditional comets, but human analysis revealed the statistical clustering that makes their simultaneous arrival noteworthy. Similarly, 3I Atlas was initially identified by automated detection algorithms, but its interstellar nature became apparent only through careful human analysis of its orbital characteristics. The combination of computational power and human insight maximizes our chances of recognizing truly significant discoveries. The educational implications of this collaboration extend beyond astronomy to all fields that rely on data analysis and pattern recognition. Students learning to work with large data sets need skills in both computational analysis and critical thinking about what patterns might actually mean. The false discovery rate in modern science reflects partly the challenge of finding genuine signals in the noise of massive data sets. When researchers test thousands of potential correlations, some will appear statistically significant purely by chance, regardless of any underlying causal relationships. Protecting against false discoveries requires statistical methods that account for multiple comparisons while remaining sensitive enough to detect genuine phenomena. The field of astronomical statistics has developed sophisticated tools for this purpose, but applying them correctly requires understanding both the mathematics and the physical processes being investigated. Our comet investigation demonstrates how these tools can be applied to evaluate extraordinary claims without dismissing potentially significant discoveries. The statistical analysis clearly shows that 2025's clustering exceeds normal expectations for random comet arrivals, justifying careful investigation of potential underlying causes. But the same analysis reveals no evidence for the kind of orbital correlations or behavioral synchronization that would indicate exotic coordination mechanisms. The clustering appears to be a genuine statistical outlier, that doesn't reflect hidden physics or alien intervention. This conclusion illustrates how statistical analysis can distinguish between different types of unusual observations, those that reflect measurement error or sampling bias versus those that indicate genuinely anomalous phenomena, and those that suggest new physics versus those that fall within the range of known but rare natural processes. The development of these analytical capabilities represents one of astronomy's greatest achievements over the past century. The field has evolved from purely descriptive observations to quantitative hypothesis testing that can distinguish reliably between competing explanations for unusual phenomena. This evolution parallels broader developments in scientific methodology that emphasize reproducibility, statistical rigor, and systematic bias reduction. Modern astronomy serves as a model for other observational sciences that must extract reliable signals from noisy datasets. The public communication of astronomical discoveries faces unique challenges because the subject matter naturally inspires wonder and speculation that can easily outpace available evidence. The apparent meaningfulness of celestial events taps into deep psychological patterns that have influenced human cultures throughout history. Ancient civilizations developed elaborate mythological frameworks to explain the movements of celestial objects, often attributing agency and intention to phenomena that we now understand as consequences of gravitational physics. Modern humans retain these pattern-seeking tendencies even though our scientific understanding has advanced dramatically. The challenge for contemporary science communication is channeling public fascination with cosmic mysteries toward genuine understanding rather than unfounded speculation. This requires maintaining honesty about uncertainties while demonstrating how scientific methods can distinguish between reliable knowledge and wishful thinking. The 2025 Comet experience provides an ideal opportunity to demonstrate these principles in action. The genuine statistical unusualness of 7 bright comets arriving simultaneously creates legitimate grounds for scientific curiosity, while the absence of evidence for exotic coordination illustrates how rigorous analysis can rule out sensational explanations. The process of investigation itself becomes educational, showing how astronomers approach unusual observations with appropriate skepticism while remaining open to evidence that might challenge conventional understanding. This balanced approach models intellectual humility that serves society well beyond astronomical contexts. The long-term implications of our investigation extend to fundamental questions about the nature of randomness and meaningful coincidence in a universe governed by deterministic physical laws. The apparent clustering of comet arrivals in 2025 feels meaningful to human observers, but the universe itself operates without regard for human interpretations of significance. This tension between objective physical processes and subjective human meaning-making reflects deeper philosophical questions about the relationship between scientific understanding and human experience. Science reveals how the universe works, but it doesn't address questions about why certain patterns feel meaningful to conscious observers. The study of complex systems has shown how simple deterministic rules can generate patterns that appear random or meaningful, depending on the observer's perspective and analytical tools. Weather systems, for example, follow precise physical laws but produce behaviors that seem chaotic and unpredictable over longer timescales. Solar system dynamics exhibit similar characteristics. Orbital mechanics operates with clockwork precision over short periods, but gravitational perturbations accumulate over millions of years to produce apparently random distributions of comet arrival times. The clustering we observe in 2025 might reflect subtle periodicities that operate on timescales longer than recorded human history. Future astronomical observations might reveal whether similar clustering occurs at regular intervals, possibly reflecting gravitational resonances with giant planets, or oscillations in the galaxy's gravitational field that affect the Oort cloud structure. Such discoveries would transform apparent randomness into evidence of hidden order operating on astronomical timescales. The search for such patterns requires datasets spanning much longer periods than current astronomical records provide. Paleontological evidence for periodic mass extinctions has suggested possible correlations with astronomical cycles, but the evidence remains controversial and difficult to verify. The development of more sensitive instruments and longer observational baselines will eventually provide the data needed to test these hypotheses rigorously. Space-based telescopes can monitor comet populations continuously without atmospheric interference, while improved computational models can simulate outer solar system dynamics over geological timescales. These technological advances will revolutionize our understanding of how the solar system evolved and how it continues to change over time. The 2025 comet swarm represents just one snapshot of an ongoing process that has been shaping our cosmic neighborhood for billions of years. The preservation of observational records from events like our current investigation ensures that future researchers will have access to detailed data about unusual phenomena when they develop better analytical tools. Every photograph, spectrum, and brightness measurement contributes to a growing database that will inform astronomical research for decades. The democratization of high-quality observational equipment means that amateur astronomers can contribute data that meets professional standards for accuracy and precision. CCD cameras and computerized telescopes that once cost hundreds of thousands of dollars are now available to dedicated hobbyists for a few $1,000s. This accessibility has transformed astronomy from a field dominated by a few major observatories to a distributed science involving thousands of observers worldwide. The coordinated observation campaigns for events like 3I at Lhasa perihelion passage demonstrate how this distributed network can achieve scientific objectives that would be impossible for any single institution. The social aspects of astronomical collaboration extend beyond data collection to education and public engagement. Online communities of amateur astronomers share techniques, compare observations, and collectively solve problems that individual observers might find insurmountable. These communities also serve as bridges between professional research and public understanding, translating technical discoveries into accessible explanations while maintaining scientific accuracy. The quality of amateur astronomy communication often exceeds that of traditional media outlets because it combines deep technical knowledge with genuine enthusiasm for the subject matter. The role of amateur astronomers in discovering and monitoring unusual phenomena like our comet swarm highlights the continuing importance of human observation in an era of automated surveys. While computers excel at detecting routine objects that match expected patterns, human observers often notice subtle anomalies that escape algorithmic detection. The collaborative relationship between professional and amateur astronomy will likely strengthen as both communities develop better tools for sharing data and coordinating observations. Real-time communication networks allow immediate alerts when unusual phenomena occur, enabling rapid follow-up observations that capture transient events. The scientific return on this collaboration extends beyond specific discoveries to broader questions about how science progresses in an era of massive datasets and global communication networks. The traditional model of isolated research groups working independently is giving way to distributed collaborations that can respond rapidly to new observations. This evolution mirrors broader changes in how knowledge is created and shared across all scientific disciplines. The internet has transformed science from a collection of separate specialties into an interconnected web of researchers who can access each other's data and expertise instantly. The implications for astronomical education are profound because students can now participate directly in cutting-edge research rather than simply learning about discoveries made by others. Real-time access to observational data allows classroom exercises that engage students in the actual process of scientific discovery. The investigation of our 2025 comet swarm provides an ideal example of how students can apply statistical analysis, orbital mechanics, and critical thinking to evaluate extraordinary claims about unusual phenomena. The combination of genuine scientific interest and clear analytical tools creates learning opportunities that traditional textbook exercises cannot match. These educational applications extend the impact of astronomical discoveries far beyond the scientific community to influence how society approaches questions about evidence, probability, and the distinction between correlation and causation. The analytical skills developed through astronomical investigation transfer readily to other domains where critical thinking about data and patterns proves essential. The media coverage of astronomical discoveries like our comet swarm also provides opportunities to model responsible science communication that maintains public interest while avoiding sensational misrepresentation. The challenge lies in presenting uncertainty and statistical analysis in ways that engage rather than confuse general audiences. The success of science communication efforts increasingly depends on understanding how different audiences process information about probability and risk. Research in cognitive psychology reveals systematic biases that affect how people interpret statistical information, particularly when dealing with low-probability events that might have high-impact consequences. The framing of uncertainty becomes crucial in maintaining public trust in scientific institutions, while avoiding both false alarm and inappropriate complacency. The 2025 Comet investigation demonstrates how careful analysis can acknowledge genuine unusualness without promoting unfounded speculation about exotic causes. This balanced approach serves as a template for communicating about other phenomena that combine statistical unusualness with potential for misinterpretation, from earthquake swarms to disease outbreaks to technological failures that might seem coordinated but actually reflect independent causes. The development of better science communication strategies benefits not only public understanding, but also scientific research itself by creating more informed audiences capable of supporting the kinds of long-term observational programs that produce major discoveries. Astronomy's unique position as a science that inspires wonder while demanding rigorous analysis makes it an ideal vehicle for teaching broader lessons about how knowledge advances through careful observation and hypothesis testing. The cosmic perspective that astronomy provides helps people understand their place in a universe governed by comprehensible physical laws. The continuing investigation of phenomena like our 2025 comet swarm ensures that astronomy will keep providing opportunities for genuine discovery, alongside educational experiences that strengthen society's capacity for critical thinking about complex problems. Thank you for joining us on Simply About Earth for this comprehensive investigation into one of astronomy's most intriguing mysteries. The 2025 comet swarm continues to unfold before our eyes, offering months of spectacular observing opportunities and valuable scientific insights. Whether you're observing from light-polluted cities or pristine dark sites, this cosmic celebration reminds us that the universe still holds surprises for those patient enough to watch and wise enough to wonder. As we've seen throughout this investigation, the intersection of statistical analysis, pattern recognition, and human psychology creates complex challenges for understanding unusual phenomena. The 7-comet convergence of 2025 represents a legitimate statistical outlier that justifies scientific attention while demonstrating how extraordinary claims require extraordinary evidence. The absence of evidence for exotic coordination between 3I Atlas and our traditional comets doesn't diminish the profound value of this natural experiment in comparative astronomy. Multiple bright comets appearing simultaneously provide research opportunities that occur perhaps once in a generation, advancing our understanding of outer solar system dynamics and comet physics in ways that isolated observations cannot achieve. The enhanced solar activity that accompanies solar maximum conditions adds another layer of complexity and spectacle to our cosmic show. The same coronal mass ejections that threaten technological infrastructure create dramatic tail disconnections and plasma instabilities that make 2025 an exceptional year for comet photography and space weather research. The distributed observation campaigns, coordinated by professional and amateur astronomers worldwide, demonstrate how modern science increasingly relies on collaborative networks that transcend institutional boundaries. Every photograph, spectrum, and brightness measurement contributes to a growing database that will inform astronomical research for decades to come. The educational implications of this investigation extend far beyond astronomy to fundamental questions about how we evaluate unusual claims and distinguish between meaningful patterns and statistical coincidences. The analytical tools we've applied to our comet investigation transfer readily to other domains where critical thinking about data and evidence proves essential. The technological progress that enables modern astronomical discovery continues accelerating the pace of exploration while creating new opportunities for serendipitous observations. Automated sky surveys operating continuously around the world ensure that we'll detect future phenomena like our 2025 swarm, while improved analytical tools help us understand what these discoveries actually mean. The challenge for future researchers will be developing frameworks sophisticated enough to distinguish between genuine anomalies and the kind of apparent clustering that emerges naturally from increasingly large data sets. Machine learning algorithms and statistical analysis provide powerful tools for this purpose, but they require careful application to avoid both false discoveries and missed opportunities for genuine breakthroughs. The human element remains crucial in astronomical research because pattern recognition often reveals subtle relationships that escape algorithmic detection. The collaborative relationship between computational efficiency and human insight maximizes our chances of recognizing truly significant discoveries while avoiding premature conclusions about unusual observations. The media environment surrounding astronomical discoveries creates both opportunities and challenges for science communication. The democratization of content creation allows broader participation in scientific discourse while requiring more sophisticated strategies for maintaining factual accuracy in competition with sources that prioritize engagement over evidence. Educational institutions bear particular responsibility for teaching critical thinking skills that help students evaluate extraordinary claims against appropriate evidence standards. The ability to distinguish between correlation and causation, understand statistical probability, and recognize the difference between speculation and established fact serves society well beyond astronomical contexts. The 2025 Comet Experience provides an ideal case study for exploring these concepts because it combines genuine statistical unusualness with clear observational data that can be analyzed objectively. Students can examine the same evidence that professional astronomers use and reach their own conclusions about whether exotic explanations are warranted. The psychological aspects of pattern recognition deserve continued investigation because they affect how both professional researchers and the general public interpret unusual phenomena. Understanding cognitive biases that influence temporal coincidence interpretation helps develop better analytical tools and communication strategies. The institutional safeguards that professional astronomy has developed against premature conclusions about unusual observations, peer review, independent verification, and statistical analysis provide templates for other fields dealing with complex data and potential false discoveries. The long-term implications of our investigation extend to fundamental questions about the nature of randomness and meaningful coincidence in a universe governed by deterministic physical laws. The apparent clustering of comet arrivals feels meaningful to human observers, but the universe operates without regard for human interpretations of significance. Future observations might reveal whether similar clustering occurs at regular intervals, possibly reflecting gravitational resonances or galactic influences that operate on timescales longer than recorded human history. Such discoveries would transform apparent randomness into evidence of hidden order operating on astronomical scales. The preservation of detailed observational records from events like our current investigation ensures that future researchers will have access to high-quality data when they develop better analytical tools. The collaborative networks established for monitoring the 2025 swarm will continue providing valuable infrastructure for future astronomical investigations. The scientific method's power to distinguish between reliable knowledge and wishful thinking becomes particularly evident when applied to phenomena that inspire wonder and speculation. The cosmic perspective that astronomy provides helps people understand their place in a universe that operates according to comprehensible physical laws while remaining vast enough to produce genuine surprises. The continuing evolution of astronomical observation and analysis ensures that we'll keep discovering phenomena that challenge our understanding while providing opportunities for educational experiences that strengthen society's capacity for critical thinking about complex problems. As our investigation concludes, we're reminded that the universe provides enough authentic mystery to occupy human curiosity for millennia, without requiring us to invent additional puzzles based on pattern-seeking psychology. The 7 independent comets converging through natural processes while an interstellar visitor makes its first and only passage through our solar system represents a cosmic coincidence worth celebrating for its own remarkable timing. The tools we've developed for evaluating extraordinary claims about celestial coordination will serve us well when future astronomical discoveries challenge conventional understanding. The balance between appropriate skepticism and openness to evidence that might contradict expectations represents science's greatest strength in distinguishing between genuine discoveries and attractive speculation. Keep looking up, and remember that the most profound discoveries often hide in plain sight, waiting for careful observers to notice patterns that reveal the elegant clockwork of celestial mechanics. The cosmos rewards our curiosity with beauty, mystery, and understanding in equal measure, and the investigation continues with every clear night and every new observation. Whether you're tracking these comets with sophisticated equipment or simply stepping outside to witness their passage with naked eyes, you're participating in humanity's ongoing dialogue with the universe, a conversation conducted through careful observation, rigorous analysis, and the endless wonder that drives us to keep asking questions about our place in the cosmic scheme. The 2025 comet swarm will fade from view as our visitors complete their solar encounters and return to the outer darkness. But the lessons learned from this investigation will inform astronomical research and science education for generations to come. The universe has given us a gift: 7 messengers from the outer solar system and 1 visitor from the stars, arriving together to remind us that reality often exceeds the creativity of speculation, and that careful observation rewards us with discoveries that no amount of wishful thinking could imagine. But before we conclude our investigation, we need to examine the broader historical context that makes the 2025 comet swarm truly exceptional. Throughout recorded human history, astronomical events have served as catalysts for scientific revolution, cultural transformation, and technological advancement. The convergence we're witnessing may represent such a pivotal moment, not because of exotic coordination, but because of how it challenges our understanding of statistical probability and cosmic coincidence. The ancient Chinese maintain the most comprehensive historical records of comet appearances, documenting observations that span over 2 millennia. These meticulous chronicles reveal patterns of clustering and isolation that mirror what we observe in modern astronomical surveys. Periods of enhanced comet activity alternated with decades of relative quiet, creating rhythms that ancient astronomers interpreted through the lens of dynastic cycles and celestial mandate. The Han Dynasty records describe the Year of 7 Stars, a legendary period when multiple celestial visitors appeared simultaneously, interpreted as harbingers of imperial transition. While modern analysis cannot verify the astronomical accuracy of these ancient accounts, they demonstrate that clustering phenomena have captured human attention across cultures and centuries. Medieval Islamic astronomers developed sophisticated mathematical tools for predicting comet returns, building upon Greek geometric principles while incorporating observational techniques that wouldn't be matched in Europe for centuries. Their calculations revealed periodicities in certain comet families that suggested underlying gravitational relationships, early glimpses of the orbital mechanics that Newton would later formalize into universal laws. The European Renaissance brought new observational instruments and analytical methods that transformed comet studies from descriptive chronicling to predictive science. Tycho Brahe's precise measurements of comet positions demonstrated that these objects moved beyond the lunar sphere, contradicting Aristotelian cosmology and preparing the ground for Copernican revolution. Johannes Kepler's analysis of comet orbits revealed the same elliptical patterns that governed planetary motion, suggesting universal gravitational principles that operated throughout the solar system. His work laid the foundation for understanding how gravitational perturbations could cluster comet arrivals through resonance effects and chaotic dynamics. The invention of the telescope revolutionized comet observation by revealing structural details invisible to naked-eye observers. Galileo's sketches of comet nuclei and tail development provided the first scientific documentation of how solar heating transforms dormant ice chunks into spectacular celestial displays. Edmund Halley's prediction of his namesake comet's return in 1758 marked astronomy's transition from descriptive to predictive science. The successful verification of his calculation demonstrated that celestial mechanics operated according to mathematical laws that could be understood and applied by human intelligence. The statistical analysis of comet discovery rates began in earnest during the 19th century, as systematic sky surveys produced increasingly comprehensive catalogues of orbital elements. These early investigations revealed the same clustering patterns that characterize our 2025 swarm: periods of enhanced activity, separated by intervals of relative quiet. The development of photographic astronomy in the late 1800s exponentially increased the sensitivity of comet searches while providing permanent records that could be analyzed years or decades after initial observations. These photographic archives now span more than a century, creating the longest continuous database of comet discoveries in human history. The introduction of electronic detectors in the mid-20th century further revolutionized astronomical observation by enabling precise photometry and spectroscopy of objects too faint for photographic detection. Modern CCD cameras can detect individual photons with quantum efficiency approaching theoretical limits, revealing details of comet composition and behavior that were unimaginable to earlier generations of astronomers. Space-based observations have eliminated atmospheric interference while providing access to wavelengths blocked by Earth's atmosphere. Infrared telescopes reveal the thermal signatures of comet nuclei and dust production rates, while ultraviolet instruments detect the hydrogen envelopes that betray comet activity long before visible signs appear. The comprehensive nature of modern comet surveys means that our 2025 clustering represents the first time in history that we can be confident we're observing a complete sample of bright comets arriving within a specific time window. Earlier apparent clusterings might have reflected observational bias or incomplete sky coverage rather than genuine statistical anomalies. This completeness transforms our investigation from historical curiosity to rigorous statistical analysis that can distinguish between random clustering and potentially significant patterns. The mathematical tools available to contemporary astronomers, Monte Carlo simulations, Bayesian analysis, and machine learning algorithms provide unprecedented capability for extracting meaningful signals from complex datasets. The application of these tools to historical comet records reveals fascinating patterns that span centuries or millennia. Some clustering appears to correlate with solar activity cycles, others with galactic orbital periods, and still others with no discernible pattern beyond the statistical fluctuations expected in any random process. The search for long-term periodicities in comet arrivals connects to broader questions about how the solar system responds to external influences. Our Sun orbits the galactic center with a period of approximately 225 million years, passing through regions of varying stellar density and gravitational influence that could affect the Oort cloud structure. Theoretical models suggest that close encounters with other stars or passage through the galactic disk could trigger episodes of enhanced comet activity by gravitationally perturbing objects in the outer solar system. These interactions operate on timescales vastly exceeding human historical records, but they might leave detectable signatures in the geological record through correlation with mass extinction events. The controversial hypothesis, linking periodic mass extinctions to astronomical cycles, remains actively debated because the evidence spans multiple scientific disciplines: paleontology, geology, astronomy, and statistics, each with different standards for evaluating extraordinary claims. The integration of such diverse evidence requires analytical frameworks that can accommodate uncertainty while avoiding premature conclusions. Our investigation of the 2025 comet swarm exemplifies this interdisciplinary approach by combining orbital mechanics, statistical analysis, observational astronomy, and cognitive psychology to evaluate claims about unusual phenomena. The methodology we've developed could serve as a template for investigating other apparent patterns that span multiple timescales and observational domains. The technological infrastructure required for comprehensive comet monitoring continues expanding as new survey telescopes come online and space-based observatories extend our observational reach. The Vera Rubin Observatory, scheduled to begin operations in the mid-2020s, will scan the entire visible sky every few nights with unprecedented sensitivity and precision. This next-generation survey capability will increase comet discovery rates by orders of magnitude, while providing the temporal resolution needed to detect clustering patterns on shorter timescales. The resulting database will contain millions of objects with precisely determined orbits, creating opportunities for statistical analysis that were impossible with smaller samples. The challenge of analyzing such massive datasets requires new computational approaches that can identify meaningful patterns without being overwhelmed by spurious correlations. Machine learning algorithms excel at classification tasks, but they require careful training to avoid missing genuinely unusual phenomena that don't match expected patterns. The collaboration between human insight and computational power becomes increasingly important as data volumes exceed what individual researchers can analyze manually. The most successful astronomical discoveries often result from creative human interpretation of patterns that automated systems identified but couldn't understand. The 2025 Comet investigation demonstrates this human-computer synergy by using automated surveys to discover most of our cast members, while relying on human analysis to recognize the statistical clustering that makes their simultaneous arrival noteworthy. Neither purely automated nor purely manual approaches would have revealed the full significance of this phenomenon. The educational implications of this collaboration extend beyond astronomy to all fields dealing with big data and pattern recognition. Students learning to work with large datasets need skills in both computational analysis and critical thinking about what apparent patterns might actually mean. The false discovery rate in modern science partly reflects the challenge of finding genuine signals in the noise of massive datasets. When researchers test thousands of potential correlations, some will appear statistically significant purely by chance, regardless of any underlying causal relationships. Protecting against false discoveries requires statistical methods that account for multiple comparisons while remaining sensitive enough to detect genuine phenomena. The field of astronomical statistics has developed sophisticated tools for this purpose, but applying them correctly requires understanding both the mathematics and the physical processes being investigated. The integration of these analytical tools into undergraduate and graduate education ensures that future researchers will be better equipped to navigate the challenges of big data astronomy. The combination of theoretical knowledge and hands-on experience with real datasets prepares students for careers in an increasingly data-driven scientific landscape. The public communication of astronomical discoveries faces unique challenges in an era of social media and viral content. The apparent meaningfulness of celestial events taps into psychological patterns that make dramatic interpretations spread faster than careful analysis. The speed of information propagation often outpaces the deliberate pace of scientific verification. Educational institutions and scientific organizations bear responsibility for developing communication strategies that can compete effectively with sensational content while maintaining factual accuracy. This requires understanding how different audiences process information about uncertainty and risk, particularly when dealing with low-probability events that might have high-impact consequences. The 2025 Comet investigation provides an ideal case study for exploring these communication challenges because it combines genuine statistical unusualness with clear potential for misinterpretation. The same clustering pattern that justifies scientific attention also provides raw material for conspiracy theories and doomsday scenarios. The key to effective science communication lies in acknowledging genuine uncertainty, while demonstrating how systematic analysis can distinguish between reliable conclusions and speculative possibilities. The process of investigation becomes as educational as the final results, showing how science progresses through careful evaluation of evidence rather than acceptance of authority. The cognitive psychology research that illuminates how people interpret clustering and coincidence has direct applications to science education and public communication. Understanding the biases that affect pattern recognition helps educators develop teaching strategies that strengthen critical thinking while respecting the psychological needs that make certain interpretations appealing. The availability heuristic makes recent or dramatic events seem more probable than they actually are. Confirmation bias leads people to notice evidence supporting preferred conclusions while ignoring contradictory data, and the clustering illusion makes random patterns appear more meaningful than they actually are. These biases affect scientists as well as the general public, requiring institutional safeguards rather than individual awareness alone. The peer review process in scientific publishing specifically addresses these biases by requiring independent evaluation of research claims before publication. The system isn't perfect, but it provides crucial quality control that helps distinguish between reliable discoveries and the kind of false patterns that individual researchers might find compelling. The replication crisis affecting multiple scientific disciplines has highlighted the importance of independent verification for extraordinary claims. Phenomena that seem obviously significant to their discoverers often fail to survive scrutiny by independent research groups using different methods and assumptions. Our Comet investigation exemplifies the kind of transparent analysis that facilitates independent verification. By clearly documenting our methods, assumptions, and limitations, we enable other researchers to evaluate our conclusions using their own analytical tools and datasets. The global nature of modern astronomical research means that any significant discovery will be immediately subjected to scrutiny by researchers worldwide, each bringing different perspectives and expertise to bear on the evaluation process. This distributed verification system provides much stronger protection against false discoveries than any single institution could achieve. The technological democratization that has made high-quality astronomical instruments accessible to amateur observers also democratizes the verification process. Dedicated hobbyists can now contribute observations that meet professional standards for accuracy and precision, multiplying the number of independent observers available to confirm or refute unusual claims. The coordinated observation campaigns for events like 3I Atlas's perihelion passage demonstrate how this distributed network can achieve scientific objectives that would be impossible for any single observatory. The resulting datasets provide unprecedented detail about transient phenomena while establishing baselines for detecting genuinely anomalous behavior. The social dynamics of scientific collaboration have evolved dramatically as internet communication enables real-time coordination among researchers worldwide. Traditional barriers between professional and amateur astronomy continue dissolving as technology makes high-quality observations accessible to broader communities. This evolution creates both opportunities and challenges for maintaining scientific standards while encouraging broader participation. The enthusiasm and dedication of amateur observers often exceed what professional astronomers can sustain, given their teaching and administrative responsibilities. But amateur observations require careful quality control to meet scientific standards. The development of standardized protocols for citizen science projects helps address these quality concerns while maximizing the scientific value of amateur contributions. Clear guidelines for instrument calibration, observation procedures, and data reporting ensure that amateur observations can be integrated seamlessly with professional datasets. The Variable Star Observers Organization has pioneered many of these approaches through decades of coordinating amateur contributions to stellar astronomy. Their protocols for photometry, data validation, and quality control provide templates that other fields can adapt for their specific needs. The application of similar approaches to comet observations would dramatically expand our monitoring capabilities while engaging broader communities in the process of scientific discovery. The 2025 swarm provides an ideal opportunity to test these collaborative frameworks under conditions of high public interest and scientific importance. The long-term scientific legacy of our investigation will depend partly on how successfully we document not just our conclusions, but also the reasoning process that led to them. Future researchers studying similar phenomena will benefit from understanding both what we discovered and what led us down particular analytical paths. The preservation of complete observational datasets, including null results and failed hypotheses, ensures that future analysts won't repeat our mistakes while enabling them to apply new analytical tools to our original data. The history of science shows that important discoveries often emerge from reanalysis of existing datasets using improved methods or theoretical frameworks. The digital preservation of astronomical data presents technical challenges that require ongoing attention as storage technologies evolve and file formats become obsolete. Professional observatories maintain dedicated data archives with migration policies designed to ensure long-term accessibility, but smaller datasets from amateur observers often lack such institutional support. The development of distributed archiving systems could address these preservation challenges while making observational data more widely accessible to researchers worldwide. Cloud storage technologies provide scalable solutions that could democratize access to historical observations currently locked in institutional archives. The standardization of data formats and metadata schemas would facilitate the integration of observations from different sources while ensuring that future researchers can understand and utilize historical datasets. The International Virtual Observatory Alliance has made progress toward these goals, but broader adoption requires continued coordination among diverse astronomical communities. The philosophical implications of our investigation extend beyond technical questions about data analysis to fundamental issues about the nature of scientific knowledge and the role of chance in natural phenomena. The apparent clustering of comet arrivals challenges our intuitive understanding of randomness, while demonstrating how statistical analysis can distinguish between meaningful patterns and coincidental arrangements. The tension between objective physical processes and subjective human interpretation reflects deeper questions about the relationship between scientific understanding and conscious experience. Science reveals how the universe operates, but it doesn't address questions about why certain patterns feel meaningful to observers or what constitutes sufficient evidence for accepting extraordinary claims. The study of complex systems has shown how simple deterministic rules can generate behaviors that appear random or meaningful, depending on the observer's perspective and analytical tools. Weather systems follow precise physical laws but produce patterns that seem chaotic over longer timescales, while stock market fluctuations emerge from countless individual decisions, yet exhibit statistical regularities that suggest underlying structure. Solar system dynamics exhibit similar characteristics. Orbital mechanics operates with clockwork precision over short periods, but gravitational perturbations accumulate over millions of years to produce apparently random distributions of arrival times. The clustering we observe in 2025 might reflect subtle periodicities that operate on timescales longer than human civilization. The search for such hidden periodicities requires analytical tools that can detect weak signals in noisy data while avoiding the false patterns that emerge from random fluctuations. Fourier analysis, wavelet transforms, and other signal processing techniques provide powerful approaches to these problems, but they require careful application to astronomical data where sampling rates and observation windows may not be optimal. The development of new mathematical tools specifically designed for astronomical time series analysis represents an active area of research that could revolutionize our understanding of long-term solar system behavior. Machine learning approaches show particular promise for detecting subtle patterns that might escape traditional statistical methods. The application of these emerging analytical tools to historical comet records could reveal periodicities or correlations that previous investigations missed. The growing availability of computational resources makes it feasible to perform exhaustive searches for patterns across multiple timescales and parameter ranges. However, the statistical challenges of multiple hypothesis testing become even more severe when applied to such comprehensive searches. The probability of finding spurious patterns increases dramatically when testing thousands of potential correlations, requiring sophisticated correction methods to maintain acceptable false discovery rates. The balance between exploratory data analysis and confirmatory hypothesis testing remains one of the most challenging aspects of modern astronomical research. The same datasets used to identify potential patterns cannot provide independent confirmation of their significance, requiring either additional observations or careful statistical approaches that account for the selection effects inherent in pattern discovery. Our investigation of the 2025 comet swarm illustrates these methodological challenges while demonstrating how transparent analysis can distinguish between preliminary observations and validated conclusions. The statistical clustering we've documented provides grounds for continued investigation, but it doesn't constitute proof of any specific underlying mechanism. The continuing observations as our comets approach perihelion will provide additional data that could either strengthen or weaken the case for genuine anomalous behavior. The power of scientific method lies partly in its self-correcting nature. Continued observation can reveal when initial conclusions were premature or when genuine phenomena deserve more attention. The institutional structures that support long-term astronomical research ensure continuity across the careers of individual researchers and the lifespans of specific projects. Observatory archives maintain datasets for decades, while professional societies coordinate observation campaigns that span multiple institutions and countries. These collaborative frameworks will preserve the scientific legacy of our investigation, while enabling future researchers to build upon our preliminary conclusions. The questions we've raised about statistical clustering and cosmic coincidence will continue motivating research long after the 2025 comets fade from view. The broader implications for understanding complex systems, pattern recognition, and the role of chance in natural phenomena extend far beyond astronomy to fields ranging from epidemiology to financial analysis. The analytical tools and methodological approaches we've developed for evaluating astronomical clustering could find applications wherever researchers need to distinguish between genuine signals and statistical artifacts. The educational value of our investigation will continue growing as its methodology gets incorporated into curricula that teach critical thinking about data analysis and pattern recognition. The combination of genuine scientific interest and clear analytical frameworks creates learning opportunities that traditional textbook exercises cannot match. The public engagement generated by unusual astronomical events like our comet swarm demonstrates the continuing power of cosmic phenomena to inspire wonder while teaching important lessons about scientific reasoning. The challenge lies in channeling that inspiration toward deeper understanding rather than superficial sensationalism. The 2025 experience will likely influence how astronomers approach future investigations of unusual clustering or correlation patterns. The framework we've established for evaluating extraordinary claims while remaining open to genuine discoveries provides a template that can be adapted to other phenomena that challenge conventional understanding. The technological infrastructure developed for monitoring our comet swarm will continue providing valuable capabilities for detecting and analyzing transient astronomical phenomena. The coordinated observation networks and real-time communication systems established for this investigation create lasting improvements to our collective observational capabilities. The data analysis tools and statistical methods we've applied to the clustering problem will find applications in other areas of astronomy, where pattern recognition and significance testing play crucial roles. The experience gained through this investigation strengthens the astronomical community's capacity for addressing similar challenges in the future. The international collaboration fostered by shared interest in our unusual comet year demonstrates how astronomical phenomena can unite researchers across cultural and political boundaries. The universal appeal of cosmic mysteries transcends the divisions that separate humans in other contexts, creating opportunities for cooperation that benefit all participants. The documentation of our investigation process, including both successful approaches and dead ends, provides valuable guidance for future researchers tackling similar problems. The history of science shows that understanding why certain approaches failed can be as important as documenting what eventually succeeded. As we conclude this comprehensive analysis of the 2025 comet swarm, we're left with a deeper appreciation for both the power and limitations of scientific investigation when applied to unusual phenomena. The statistical clustering we've documented exceeds normal expectations for random arrivals, justifying continued attention while illustrating how extraordinary claims require extraordinary evidence. The absence of evidence for exotic coordination mechanisms doesn't diminish the profound scientific and educational value of witnessing 7 bright comets arrive simultaneously, while an interstellar visitor makes its first and only passage through our solar system. This natural coincidence provides research opportunities and public engagement experiences that occur perhaps once in a generation. The analytical framework we've developed for evaluating potential connections between 3I Atlas and traditional solar system comets will serve astronomy well when future observations challenge conventional understanding. The balance between appropriate skepticism and openness to evidence represents scientific method at its best, rigorous enough to avoid false discoveries, yet flexible enough to recognize genuine phenomena when extraordinary evidence finally appears. The broader lessons about pattern recognition, statistical analysis, and the psychological factors that influence interpretation of unusual events extend far beyond astronomy to any field where humans must distinguish between meaningful signals and random noise. The cognitive biases we've identified affect all areas of human decision-making, making the analytical tools we've developed broadly applicable to critical thinking in an uncertain world. The technological and methodological advances stimulated by our investigation will continue benefiting astronomical research long after the 2025 comets complete their solar encounters. The collaborative networks, observation protocols, and analysis techniques developed for this project create lasting improvements to our capacity for studying transient phenomena and evaluating extraordinary claims. The educational impact of our investigation demonstrates how unusual astronomical events can serve as powerful teaching tools that engage public interest while illustrating fundamental principles of scientific reasoning. The combination of genuine mystery and rigorous analysis creates learning opportunities that traditional approaches to science education cannot match. The international scope of our investigation showcases astronomy's unique ability to unite researchers and observers worldwide in pursuit of common understanding. The cosmic perspective that emerges from studying phenomena that transcend terrestrial boundaries helps humanity recognize shared interests that extend beyond political and cultural divisions. Until next time, this is Simply About Earth, encouraging you to keep exploring, keep questioning, and keep marveling at the magnificent complexity of our cosmic home. The universe continues revealing its secrets to those patient enough to observe carefully and wise enough to distinguish between what we can know with confidence and what remains tantalizingly beyond our current understanding. Remember that every clear night offers opportunities for discovery, whether you're tracking comets with sophisticated equipment or simply stepping outside to witness the majesty of a star-filled sky. The cosmos rewards curiosity with beauty, mystery, and understanding in equal measure, and there's always more to learn for those willing to look up and wonder what secrets await discovery in the vast darkness between the stars.